Please subscribe to support the channel. Throughout the cosmos, there are stars that dazzle with their brilliance, stars that form in clusters, and stars that live quiet, steady lives. But then there are the exceptions, the ones that defy expectations, the ones that carry with them stories of violence, speed, and mystery. Zeta Ophiuchi is one of those stars. Astronomers often describe it as one of the strangest stars they have ever studied, and for good reason. Unlike most stars that remain gravitationally bound to their birthplace, Zeta Ophiuchi is on the run. It's what scientists call a runaway star, a massive, searing hot giant careening through the galaxy at incredible speeds. What makes this so fascinating is not just the fact that Zeta Ophiuchi is fast, but the mystery of why it's racing at all. Stars don't just fling themselves across the Milky Way for no reason. Something dramatic happened in its past to set it on this course, and astronomers have been piecing together that story for decades. Each new observation, whether it comes from telescopes on the ground or space-based observatories like Spitzer, adds another fragment to its puzzle. And yet, despite all the data collected, Zeta Ophiuchi continues to resist complete understanding. Its runaway status hints at a violent history. Its unusual bow shock suggests powerful interactions with the interstellar medium. And its incredible size and energy output foretell an equally dramatic end. Unlike our Sun, which enjoys a long, stable life, Zeta Ophiuchi is a star of extremes. Fast, unstable, and destined for a spectacular fate. This duality, between what we know and what still eludes us, makes Zeta Ophiuchi not just another star in the sky, but one of the most mysterious and captivating objects in the universe. It's not simply a glowing point of light, it's a cosmic wanderer, carrying scars of its past and secrets of its future. For astronomers, it's both a scientific challenge and a source of wonder. For storytellers, it's a perfect reminder that the universe is not static, but alive with drama. Zeta Ophiuchi may be mysterious in its behavior and violent in its past, but to understand it fully, we must first place it in the sky. This star lives in a part of the heavens known as Ophiuchus, the constellation of the Serpent Bearer. For stargazers, Ophiuchus rests along the celestial equator, wedged between more widely celebrated neighbors like Scorpius with its famous red supergiant Antares, or Hercules with its mythological weight. Unlike those constellations, Ophiuchus doesn't typically dominate the spotlight, yet within its boundaries lies one of the galaxy's most intriguing fugitives. Zeta Ophiuchi is nestled right there, about 366 light-years away from Earth. That number might seem abstract, but when translated into the language of light, it becomes something more profound. When you look at Zeta Ophiuchi, you are not seeing it as it is now, you are witnessing it as it appeared over 3.5 centuries ago. The photons reaching your eyes tonight set out from the star in the 1600s, when human history was moving through revolutions, discoveries, and wars. Light travels at nearly 300,000 kilometers per second, yet it still takes centuries to cross the gulf of space between Zeta Ophiuchi and us. In this sense, every glance at it is a kind of time travel, a reminder that the night sky is not static, but a living record of the past. This position in the sky is significant for several reasons. First, its location in Ophiuchus places it against a backdrop dense with cosmic activity. The Milky Way runs nearby, spilling stars, nebulae, and clusters across the region. The star itself lies slightly above the plane of the galactic disk, meaning astronomers have a relatively clear view of it without as much intervening dust as would obscure stars deeper in the galactic core. That clarity has allowed us to observe not only the star itself but also the extraordinary bow shock it produces, a vast arc of glowing dust and gas that becomes visible in the infrared spectrum. If Zeta Ophiuchi had been positioned deeper within a dustier region, that bow shock might have remained hidden, depriving us of one of the most spectacular cosmic sights connected to a single star. Its placement in Ophiuchus also threads it into layers of mythology. The constellation has long been associated with Asclepius, the healer of Greek myth who was said to have learned the secrets of life and death from a serpent. In the sky, Ophiuchus is depicted grasping the serpent's serpents, symbolizing both the struggle and mastery over forces beyond ordinary human control. To think of Zeta Ophiuchi burning fiercely in that constellation adds a poetic dimension. A star violently expelled from its home, now streaking across the heavens, residing in the house of the serpent bearer. This imagery blends myth with science, reminding us that the stars we study today with telescopes are the same stars that inspired myths thousands of years ago. From a galactic perspective, its location is also important because astronomers can use it as a reference point. By tracking its motion through the constellation, they can calculate its velocity and trace its trajectory backward in time. This backward tracing has led to one of the most fascinating discoveries about the star. It almost certainly originated elsewhere in the galaxy, in a stellar nursery rich with massive stars, before being ejected. Its current coordinates in Ophiuchus are essentially a waypoint along its journey, not its birthplace. If you could roll back the clock of galactic motion, you would watch Zeta Ophiuchi tear away from its former home, possibly in the company of a massive supernova that destroyed its stellar partner. Even though Zeta Ophiuchi's position is well charted, there's something haunting about knowing that it doesn't belong where it is now. Most stars we see in constellations are bound members of their galactic neighborhoods. They formed near where they shine today and will remain there until they eventually fade. But Zeta Ophiuchi is a wanderer, a displaced giant that streaked across space to arrive where we now observe it. When you find it in Ophiuchus, you're not looking at a star comfortably seated in its celestial family, but at a guest passing through, a cosmic refugee carrying with it a history of loss and violence. What makes its distance of 366 light-years especially fascinating is how close that really is in galactic terms. The Milky Way is over 100,000 light-years across, with many stars tens of thousands of light-years from Earth. Against that backdrop, Zeta Ophiuchi is practically in our neighborhood. Its proximity makes it an excellent laboratory for astronomers, because it's not only bright enough to study but also close enough that its structures, such as its bow shock and surrounding dust, can be observed with clarity. When NASA's Spitzer space telescope captured images of the star, the glowing arc of its bow shock appeared dramatically, a feature that would have been blurred beyond recognition if the star were even 1,000 light-years farther away. The fact that it happens to be relatively close means we can study runaway stars in far greater detail than otherwise possible. Its place in Ophiuchus also adds an observational layer for stargazers. This constellation, although not among the zodiac signs officially used in Western astrology, actually straddles the ecliptic, meaning the sun passes through it each year. That makes Zeta Ophiuchi part of a constellation deeply tied to celestial pathways. To the naked eye, Ophiuchus spreads across a wide swath of the sky, and Zeta Ophiuchi sits as one of its more luminous members. Knowing this, amateur astronomers often target it as an entry point into the mysteries of massive stars. With a decent star chart and dark skies, you can stand beneath the stars, gaze into Ophiuchus, and know that you're staring at one of the most enigmatic giants the galaxy has to offer. In sum, the location of Zeta Ophiuchi in Ophiuchus at 366 light-years away is not merely a set of coordinates. It is a story written in distance, light, and time. It is the place where a runaway star happens to be now, though it is not where it began, and certainly not where it will end. Its presence in the Serpent-bearer ties it to myths of healing and transformation, while its physical distance links it to centuries of history here on Earth. Every photon from Zeta Ophiuchi that arrives at our planet carries with it both scientific data and a silent reminder that this star, for all its power and speed, is still visible to us, still part of our human story of gazing upward, searching for meaning, and trying to piece together the mysteries of the cosmos. When we talk about stars in astronomy, many people immediately think of the brightest jewels of the night sky, Sirius blazing in Canis Major, Betelgeuse glowing red in Orion, or Vega shimmering in the Lyra constellation. Compared to these, Zeta Ophiuchi does not announce itself with overwhelming brilliance. It isn't the kind of star that demands your attention at first glance. Instead, it waits quietly for those who are willing to seek it out, rewarding careful stargazing under the right conditions. Despite being an incredibly massive and energetic star, Zeta Ophiuchi's distance from Earth and its location in a somewhat overlooked constellation make it less famous than its brighter counterparts. Yet, the simple fact that you can still see it with the naked eye, without the aid of a telescope, is a humbling reminder of just how powerful and luminous it truly is. To put this into perspective, Zeta Ophiuchi has an apparent magnitude of around 2.6. For those unfamiliar with the astronomical magnitude scale, this number might not immediately resonate, but it's worth unpacking. The scale works in reverse. The lower the number, the brighter the object appears. For example, Sirius, the brightest star in the sky, shines at magnitude -1.46, while stars at magnitude 6 are at the very limit of what the human eye can perceive in perfectly dark skies. Zeta Ophiuchi's 2.6 means it's not a showstopper, but it comfortably clears the threshold of naked eye visibility. Under a rural sky far from city lights, you can find it with ease once you know where to look. Even in suburban conditions with some light pollution, it remains visible, though it can blend into the dense background of the Milky Way if one isn't careful in identifying it. Its visibility becomes even more fascinating when we remember just how far away it is. At a distance of 366 light-years, its light has weakened considerably by the time it reaches us. For it to still shine brightly enough to be seen without instruments means it must be extraordinarily powerful at its source. In fact, astronomers calculate that Zeta Ophiuchi radiates about 65,000 times more energy than our Sun. If you could somehow swap the Sun for Zeta Ophiuchi and place it at the center of our solar system, Earth would be incinerated almost instantly, overwhelmed by the extreme radiation pouring forth from its surface. The fact that such a monster can still appear as a modest but visible star in our night sky says everything about its raw output of light and energy. For stargazers seeking Zeta Ophiuchi, the task is as much about patience and familiarity as it is about brightness. Ophiuchus itself spans a broad swath of sky along the ecliptic, meaning the Sun, Moon, and planets pass through it during the year. Zeta Ophiuchi sits within this constellation, and locating it often involves finding the neighboring bright red star Antares in Scorpius and then sweeping your eyes upward and slightly eastward into Ophiuchus. Once identified, Zeta Ophiuchi reveals itself as a blue-white point of light, its color betraying its intense surface temperature. Unlike the red glow of Antares or Betelgeuse, or the golden hue of Aldebaran, Zeta Ophiuchi has the distinct icy brilliance of a hot, young star burning its fuel at a furious rate. That contrast alone can make it a striking find for careful observers. There is also a poetic beauty in the way Zeta Ophiuchi is visible. It's not overwhelming, not obvious, and not screaming for attention. Instead, it quietly waits among the thousands of stars scattered across Ophiuchus, asking the observer to know the sky a little better, to search with intention rather than chance. For those who succeed, the reward is not just another point of light but the knowledge that they are gazing upon one of the most extraordinary stars ever studied. That awareness changes the experience. Suddenly, what appears as an ordinary star is revealed as a runaway giant, a displaced survivor of cosmic violence, carrying an invisible story written in its speed, radiation, and bow shock. For centuries, cultures observing the sky would have seen Zeta Ophiuchi without understanding its true nature. To them, it was another star contributing to the shape of Ophiuchus, blending into the mythological figure of the serpent-bearer. Only with modern astronomy have we begun to peel back the layers of its mystery. Today, every person who steps outside on a clear, dark night and points their gaze toward this constellation can experience a direct connection to this mystery. They don't need a telescope or even binoculars, just eyes and a willingness to seek. That simplicity is profound. It reminds us that the universe does not always hide its secrets in the unreachable or invisible. Sometimes, even the most extraordinary stars are visible right above us, accessible to anyone willing to look up. Zeta Ophiuchi's visibility also plays a role in its scientific story. Because it can be observed directly, it becomes a bridge between professional astronomers and the general public. While most people will never see the spectacular bow shock captured in infrared images by space telescopes, they can still look at the star itself, a pale echo of its grandeur, and know they are sharing the same view as the world's most advanced observatories. This connection helps to humanize the science, to take a runaway star racing at 24 kilometers per second and bring it into the reach of human perception. It allows the story of Zeta Ophiuchi to spread not just in academic circles but in living rooms, classrooms, and stargazing gatherings across the world. In this way, Zeta Ophiuchi is both ordinary and extraordinary at once. To the casual eye, it's just another faint star among many. To the informed observer, it's a cosmic traveler, alive with energy and bearing the marks of a violent past. The fact that it is visible at all speaks to the immense scale of stellar power. It invites us to remember that behind every point of light in the night sky lies a story, some quiet and steady, others explosive and strange. And among them, few stories are as dramatic as that of Zeta Ophiuchi. When we shift our attention from Zeta Ophiuchi's visibility in the night sky to its true physical nature, the story takes on an even more dramatic dimension. That faintly glowing point of light you can spot with the naked eye is not just another ordinary star like the Sun. It belongs to one of the rarest and most extreme classes of stars in the universe. Astronomers classify it as an O-type star, a designation that immediately signals something extraordinary. These stars are the heavyweights of the cosmos, massive, blisteringly hot, and dazzlingly luminous. They are also rare, making up less than 1 in every million stars in the Milky Way. To see one with the naked eye, as we do with Zeta Ophiuchi, is to witness something statistically improbable, a cosmic outlier shining through sheer force of energy. The classification of O-type tells us several things right away. For starters, Zeta Ophiuchi is blue in color, not because it is cold, but because it is so incredibly hot that it emits most of its energy in the blue and ultraviolet parts of the spectrum. Its surface temperature soars above 30,000 Kelvin, more than 5 times hotter than the Sun's relatively mild 5,800 Kelvin. To put that in human terms, if the Sun feels like the steady warmth of a fireplace, Zeta Ophiuchi is a raging inferno blasting radiation at lethal intensities. This heat not only gives it its color but also means it pours immense amounts of ultraviolet radiation into its surroundings, shaping and altering the very space around it. Its mass is another defining feature. Zeta Ophiuchi weighs in at around 20 times the mass of our Sun. That may not sound like much at first, just 20 of something compared to 1, but when it comes to stars, mass is not just about size. Mass dictates everything: brightness, lifespan, evolution, and eventual death. A star with 20 solar masses is not simply 20 times bigger, it is thousands of times brighter and burns through its nuclear fuel at a ferocious pace. The Sun, for example, enjoys a stable lifespan of around 10 billion years, with nearly 5 billion years still to go. Zeta Ophiuchi, by contrast, will live only a few million years in total, a brief, furious flash compared to the Sun's long, steady glow. What makes this so captivating is the paradox it creates. Here we have a star that, from Earth, looks modest and unassuming compared to giants like Sirius or Betelgeuse. Yet, in reality, it outshines and outpowers most stars in the galaxy by orders of magnitude. If Zeta Ophiuchi were placed where our Sun is now, it would not appear as a faint star in the night sky. It would dominate the heavens, turning night into perpetual day, its fierce radiation stripping Earth of its atmosphere and boiling away oceans in an instant. It is only because it lies hundreds of light-years away that we can safely observe it at all. Astronomers use the term main sequence O-type to describe Zeta Ophiuchi's current stage of life. Like the Sun, it is fusing hydrogen into helium in its core, but it does so at a vastly accelerated rate. Its nuclear furnace operates at extreme pressures and temperatures, producing energy on a scale that defies human comprehension. Every second, it releases more energy than our Sun will emit over tens of thousands of years. That power not only radiates outward as light but also drives intense stellar winds, streams of charged particles blown off the star's surface at millions of kilometers per hour. These winds contribute to the bow shock phenomenon we'll explore later, carving dramatic patterns into the interstellar medium as Zeta Ophiuchi plows forward on its runaway trajectory. The O-type classification also gives us insight into its destiny. Such stars are doomed to die young, not in quiet fades but in catastrophic explosions. When Zeta Ophiuchi exhausts its hydrogen fuel, it will burn through heavier elements in rapid succession, its core collapsing under gravity until the inevitable supernova eruption. This is the fate of nearly all O-type stars, and their explosive deaths seed the galaxy with the heavy elements necessary for planets, life, and future generations of stars. In this sense, Zeta Ophiuchi is both destructive and creative. Destructive in its intensity, yet creative in the long arc of cosmic evolution, as it will one day enrich the Milky Way with the raw materials for new worlds. It is also worth reflecting on just how rare O-type stars are. Our galaxy contains an estimated 200 to 400 billion stars, yet only a few tens of thousands are O-type. They are born in dense stellar nurseries, often as part of massive star clusters, and they rarely live long enough to wander far from their birthplace. That makes Zeta Ophiuchi's status as a runaway all the more remarkable. It's not only a member of a rare stellar class, it's also a survivor of a violent event that expelled it from its original cluster, sending it careening into interstellar space. To observe one is rare enough, but to observe one that is on the move, dragging its past behind it like a trail, is a gift to astronomers. So, when we speak of the basics of Zeta Ophiuchi, we are already dealing with extremes. It is not a gentle yellow star like our Sun, but a blue giant, radiating ultraviolet light, shedding stellar winds, and living on borrowed time. Its sheer size, its blistering heat, and its extraordinary luminosity make it one of the most powerful kinds of stars known. Yet what makes it truly special is how all of these qualities converge with its runaway nature to tell a story unlike any other. From Earth, it looks ordinary enough, just another pinpoint of light in our Ophiuchus. But beneath that calm appearance lies a stellar titan, rare, violent, and magnificent, burning through its short life with reckless speed. When we shift our attention from Zeta Ophiuchi's visibility in the night sky to its true physical nature, the story takes on an even more dramatic dimension. That faintly glowing point of light you can spot with the naked eye is not just another ordinary star like the Sun. It belongs to one of the rarest and most extreme classes of stars in the universe. Astronomers classify it as an O-type star, a designation that immediately signals something extraordinary. These stars are the heavyweights of the cosmos, massive, blisteringly hot, and dazzlingly luminous. They are also rare, making up less than 1 in every million stars in the Milky Way. To see one with the naked eye, as we do with Zeta Ophiuchi, is to witness something statistically improbable, a cosmic outlier shining through sheer force of energy. The classification of O-type tells us several things right away. For starters, Zeta Ophiuchi is blue in color, not because it is cold, but because it is so incredibly hot that it emits most of its energy in the blue and ultraviolet parts of the spectrum. Its surface temperature soars above 30,000 Kelvin, more than 5 times hotter than the Sun's relatively mild 5,800 Kelvin. To put that in human terms, if the Sun feels like the steady warmth of a fireplace, Zeta Ophiuchi is a raging inferno blasting radiation at lethal intensities. This heat not only gives it its color but also means it pours immense amounts of ultraviolet radiation into its surroundings, shaping and altering the very space around it. Its mass is another defining feature. Zeta Ophiuchi weighs in at around 20 times the mass of our Sun. That may not sound like much at first, just 20 of something compared to 1. But when it comes to stars, mass is not just about size. Mass dictates everything: brightness, lifespan, evolution, and eventual death. A star with 20 solar masses is not simply 20 times bigger. It is thousands of times brighter and burns through its nuclear fuel at a ferocious pace. The Sun, for example, enjoys a stable lifespan of around 10 billion years, with nearly 5 billion years still to go. Zeta Ophiuchi, by contrast, will live only a few million years in total, a brief, furious flash compared to the Sun's long, steady glow. What makes this so captivating is the paradox it creates. Here we have a star that, from Earth, looks modest and unassuming compared to giants like Sirius or Betelgeuse. Yet, in reality, it outshines and outpowers most stars in the galaxy by orders of magnitude. If Zeta Ophiuchi were placed where our Sun is now, it would not appear as a faint star in the night sky. It would dominate the heavens, turning night into perpetual day, its fierce radiation stripping Earth of its atmosphere and boiling away oceans in an instant. It is only because it lies hundreds of light-years away that we can safely observe it at all. Astronomers use the term main sequence O-type to describe Zeta Ophiuchi's current stage of life. Like the Sun, it is fusing hydrogen into helium in its core, but it does so at a vastly accelerated rate. Its nuclear furnace operates at extreme pressures and temperatures, producing energy on a scale that defies human comprehension. Every second, it releases more energy than our Sun will emit over tens of thousands of years. That power not only radiates outward as light but also drives intense stellar winds, streams of charged particles blown off the star's surface at millions of kilometers per hour. These winds contribute to the bow shock phenomenon we'll explore later, carving dramatic patterns into the interstellar medium as Zeta Ophiuchi plows forward on its runaway trajectory. The O-type classification also gives us insight into its destiny. Such stars are doomed to die young, not in quiet fades but in catastrophic explosions. When Zeta Ophiuchi exhausts its hydrogen fuel, it will burn through heavier elements in rapid succession, its core collapsing under gravity until the inevitable supernova eruption. This is the fate of nearly all O-type stars, and their explosive deaths seed the galaxy with the heavy elements necessary for planets, life, and future generations of stars. In this sense, Zeta Ophiuchi is both destructive and creative. Destructive in its intensity, yet creative in the long arc of cosmic evolution, as it will one day enrich the Milky Way with the raw materials for new worlds. It is also worth reflecting on just how rare O-type stars are. Our galaxy contains an estimated 200 to 400 billion stars, yet only a few tens of thousands are O-type. They are born in dense stellar nurseries, often as part of massive star clusters, and they rarely live long enough to wander far from their birthplace. That makes Zeta Ophiuchi's status as a runaway all the more remarkable. It's not only a member of a rare stellar class, it's also a survivor of a violent event that expelled it from its original cluster, sending it careening into interstellar space. To observe one is rare enough, but to observe one that is on the move, dragging its past behind it like a trail, is a gift to astronomers. So, when we speak of the basics of Zeta Ophiuchi, we are already dealing with extremes. It is not a gentle yellow star like our Sun, but a blue giant, radiating ultraviolet light, shedding stellar winds, and living on borrowed time. Its sheer size, its blistering heat, and its extraordinary luminosity make it one of the most powerful kinds of stars known. Yet what makes it truly special is how all of these qualities converge with its runaway nature to tell a story unlike any other. From Earth, it looks ordinary enough, just another pinpoint of light in our Ophiuchus. But beneath that calm appearance lies a stellar titan, rare, violent, and magnificent, burning through its short life with reckless speed. When we turn our focus specifically to the size of Zeta Ophiuchi, the numbers alone are staggering. Astronomers estimate that it possesses roughly 20 times the mass of our Sun. To a casual listener, this might sound as though Zeta Ophiuchi is simply 20 times bigger, but mass in stellar terms doesn't scale in such a straightforward way. Mass in stars is not only a measure of weight or bulk, it is the single most important factor that determines a star's brightness, temperature, lifespan, and eventual fate. And in the case of Zeta Ophiuchi, that extra mass translates into a life of overwhelming energy output, but one that is destined to be brief on the cosmic timescale. For comparison, our Sun has been steadily shining for about 4.6 billion years and is expected to live for another 5 billion before it swells into a red giant and eventually becomes a white dwarf. Its modest mass gives it a slow-burning nuclear furnace, one that converts hydrogen into helium with remarkable efficiency and stability. Zeta Ophiuchi, on the other hand, with 20 solar masses packed into its core, cannot afford such patience. Its immense gravitational pressure forces nuclear fusion to occur at an accelerated rate. Instead of sipping gently from its hydrogen reserves like the Sun, Zeta Ophiuchi guzzles its fuel with ferocity, burning through it hundreds of thousands of times faster. The result is that this star, despite its grandeur, will last only about 8 million years in total, a fleeting blink compared to the Sun's 10 billion-year journey. Its size also directly influences its luminosity. While it has 20 times the mass of the Sun, its brightness is not 20 times greater. It is closer to 65,000 times more luminous. This disproportionate scaling arises because stellar luminosity increases exponentially with mass. Just as a massive bonfire burns brighter and hotter than a candle, Zeta Ophiuchi's colossal size translates into a brilliance that dwarfs nearly all of its stellar neighbors. Were it placed at the center of our solar system, its sheer radiance would flood the Earth with radiation so intense that life would be annihilated in an instant. Oceans would vaporize, atmospheres would be stripped away, and the planet would be reduced to a scorched husk. Its power is beyond anything the human imagination can comfortably grasp. What's fascinating is that the same mass that makes Zeta Ophiuchi so bright and energetic also seals its doom. High-mass stars like this cannot sustain themselves for long. Their cores, under crushing pressure, fuse hydrogen rapidly, and once that fuel is gone, they transition quickly into burning heavier elements like helium, carbon, and oxygen. Each stage burns faster than the last, pushing the star closer and closer to collapse. Eventually, when its nuclear fuel is exhausted, gravity will overwhelm the core, and the star will end its life in a spectacular supernova explosion. In this way, its mass is both its gift and its curse. It allows Zeta Ophiuchi to shine with unimaginable brilliance, but it also ensures that its time in the galaxy will be heartbreakingly short. Another way to understand the role of its mass is to consider how rare stars like Zeta Ophiuchi are. In the galaxy, small stars vastly outnumber massive ones. Red dwarfs, which are far less massive than the Sun, account for the majority of stars, and they can live for trillions of years. The heavier a star is, the less likely it is to exist, and the shorter it lives. Zeta Ophiuchi sits at the extreme end of this distribution. It is a rare gem, one of the galaxy's giants, but like a firework that explodes with brilliant intensity and then fades into darkness, its lifespan is limited by the very mass that makes it extraordinary. It is also worth noting that this enormous mass is what drives many of Zeta Ophiuchi's other distinctive features. Its strong stellar winds, streams of charged particles blown off its surface at millions of kilometers per hour, are powered by its intense radiation pressure, which in turn comes from the energy produced by its oversized core. These winds interact with the interstellar medium, creating the magnificent bow shock structure that we'll discuss later. Without its enormous mass, there would be no such phenomenon. Its runaway nature would be far less dramatic if it were a smaller, dimmer star. In other words, its size doesn't just affect its lifespan and luminosity. It shapes nearly every aspect of its interaction with the galaxy. When we step back and look at the cosmic narrative, Zeta Ophiuchi's mass becomes symbolic. It represents a choice written into the physics of the universe. Stars can be small and live long, or they can be massive and burn out quickly in a blaze of glory. There is no middle ground for giants like this. Our Sun chose longevity, giving life on Earth billions of years to emerge and evolve. Zeta Ophiuchi chose intensity, blazing with so much energy that it reshapes the very space around it. But in doing so, it has condemned itself to an early, violent death. It is a reminder that in the universe, brilliance often comes at the cost of time. So, when we say that Zeta Ophiuchi is about 20 times the mass of the Sun, we're not simply throwing out a statistic. We're highlighting the key to its entire identity. That mass makes it unimaginably bright, dangerously hot, and violently unstable. It makes it one of the galaxy's rarest and most magnificent stars, and it also ensures that it is doomed to vanish in a matter of millions of years. Its size is its destiny, and that destiny is written into every photon of light it sends across the void to reach our eyes. If Zeta Ophiuchi's sheer size and mass define its strength, then its surface temperature reveals its ferocity. This star is no gentle furnace like our Sun. Instead, its outer layers blaze at temperatures exceeding 30,000 Kelvin. To put that into perspective, our own Sun's surface is only about 5,800 Kelvin, a temperature that already provides the Earth with the warmth necessary to sustain life. Zeta Ophiuchi's surface is more than 5 times hotter, and the consequences of this temperature are immense, transforming the star into a source of blistering radiation that reshapes everything in its vicinity. At 30,000 Kelvin and above, the star's energy output shifts dramatically toward the ultraviolet part of the spectrum. While the Sun produces a modest amount of ultraviolet radiation, Zeta Ophiuchi floods space with it, unleashing torrents of high-energy photons that ionize atoms in the surrounding interstellar medium. This ultraviolet radiation strips electrons from hydrogen atoms in the clouds of gas around the star, creating glowing regions of ionized hydrogen, known as H2 regions, that can stretch across light-years of space. This is why astronomers often find massive O-type stars like Zeta Ophiuchi at the heart of bright nebulae. Their extreme temperatures light up the cosmos like cosmic lanterns, sculpting the raw materials of galaxies. To imagine this in human terms, if Earth were somehow transplanted into the vicinity of Zeta Ophiuchi, the ultraviolet radiation alone would be enough to sterilize the planet in moments. The ozone layer, our fragile shield against the Sun's much milder UV rays, would be obliterated. DNA, proteins, and all biological molecules would be shredded under the relentless bombardment of high-energy photons. Life as we know it could never exist in such proximity. This helps explain why stars like Zeta Ophiuchi, though beautiful, are also profoundly hostile. They are forces of creation and destruction, capable of triggering star formation in surrounding clouds, but also merciless to any fragile worlds that might dare orbit them. Its high surface temperature also drives the powerful stellar winds that blow outward at millions of kilometers per hour. These winds are not gentle breezes but streams of ionized gas propelled into space by the intense radiation pressure. As these winds race outward, they slam into the interstellar medium, compressing it and heating it, and in Zeta Ophiuchi's case, generating the spectacular bow shock phenomenon. Without the searing heat of its surface, those winds would not be nearly so violent, nor would they carve such dramatic shapes into the cosmic environment. Another striking consequence of such a high temperature is its spectral classification. O-type stars are defined largely by their surface temperatures, which range from about 30,000 to 50,000 Kelvin. Their spectra show lines of ionized helium and weak hydrogen absorption, telling astronomers that the photons streaming from their surfaces are so energetic that they ionize helium atoms, a process that requires extraordinary energy. Zeta Ophiuchi's spectrum confirms its status as one of these elite stars, placing it in the uppermost tier of stellar temperatures. Its blue-white glow, visible even to the naked eye, is a direct reflection of this reality. That bluish tint is nature's way of announcing just how much energy pours from its surface. When comparing Zeta Ophiuchi's temperature to the Sun's, the difference becomes more than just a number. At 5,800 Kelvin, the Sun emits most of its radiation in the visible range, with a peak in the greenish-yellow part of the spectrum. This is why sunlight appears white or yellowish to our eyes. At 30,000 Kelvin, Zeta Ophiuchi's peak radiation shifts well into the ultraviolet, a wavelength invisible to humans. What we see with our eyes as a blue-white star is just the faint visible edge of its true energy spectrum. The majority of its power is hidden from us, locked in ultraviolet and even X-ray emissions that our unaided eyes cannot perceive. This makes observing it with telescopes that can detect non-visible wavelengths crucial. Instruments like NASA's Spitzer space telescope in the infrared or the Chandra X-ray observatory reveal layers of Zeta Ophiuchi's violence that the human eye could never witness. This extraordinary heat also ties directly into its short lifespan. The hotter the star, the faster it burns its fuel, and the faster it burns its fuel, the sooner it dies. The Sun's leisurely pace means stability for billions of years. Zeta Ophiuchi's frantic pace, fueled by its blistering surface and ravenous core, guarantees an early death. Its 30,000 Kelvin surface temperature is a visible reminder that it is living life at maximum throttle, with no thought to conservation or longevity. Every photon of ultraviolet radiation is evidence of a nuclear engine that is roaring at full throttle, consuming itself in the process. But perhaps the most awe-inspiring thing about Zeta Ophiuchi's temperature is how it affects the galaxy around it. Its radiation doesn't just dissipate into space harmlessly. It reshapes its environment, carving cavities in interstellar gas, triggering new bursts of star formation, and leaving imprints that will last long after Zeta Ophiuchi itself has gone supernova. Its heat is both destructive and creative, both a death sentence for itself and a spark for future generations of stars. The 30,000 Kelvin blaze of its surface is, in many ways, the very essence of the star, violent, short-lived, and yet profoundly influential in the galactic ecosystem. So, when we describe Zeta Ophiuchi as having a surface temperature of over 30,000 Kelvin, we're not merely quoting a number from an astrophysics textbook. We are revealing the key to its nature as a cosmic furnace, one that burns too hot and too fast to survive for long. Its heat shapes everything: its light, its winds, its lifespan, and its interactions with the galaxy. That heat is the reason we see it as blue-white, the reason it floods space with ultraviolet radiation, and the reason it will one day explode in a supernova of unimaginable force. It is not just a statistic. It is the very heartbeat of Zeta Ophiuchi's mystery. One of the most astonishing aspects of Zeta Ophiuchi is not only what it is, but how it moves. Most stars in the galaxy drift quietly along with the general rotation of the Milky Way, their motions relatively modest when compared to the vast distances they cover. Our own Sun, for example, orbits the center of the galaxy at about 828,000 kilometers per hour, but relative to its neighbors it moves sedately, almost in lockstep, with little dramatic flair. Zeta Ophiuchi, however, breaks this cosmic calm. It streaks across space at a blistering speed of about 24 kilometers every single second. That's more than 50,000 miles per hour, fast enough to travel from New York to Los Angeles in less than 3 minutes. This incredible velocity sets it apart from the tranquil stars around it and immediately raises the question: what sent it hurtling through the galaxy like a cosmic missile? When astronomers measure such speeds, they usually look at two components: radial velocity, which is motion toward or away from us, and proper motion, which is motion across the sky. Zeta Ophiuchi's proper motion alone tells the story of a star that is literally fleeing its original birthplace. Over time, its position in the sky shifts noticeably against the background stars, a rare trait given how far away most stars are. Even across just a human lifetime, sensitive instruments can track Zeta Ophiuchi's relentless march, its path, cutting across Ophiuchus like a glowing trail left by an interstellar traveler. Its speed is so unusual that astronomers instantly recognized it as an outlier, a star that does not belong where it currently resides. To understand the scale of 24 kilometers per second, it helps to compare it to familiar speeds. Earth, orbiting the Sun, races through space at about 30 kilometers per second, so Zeta Ophiuchi's runaway pace is comparable to the motion of entire planets around their stars. Yet this is not orbital speed tethered to a central anchor. This is free flight, a star rushing headlong into interstellar space, unbound from its birthplace and carrying its momentum across the galaxy. It's like watching a stone flung from a sling, but on a scale where the sling is the force of a supernova and the stone is a star 20 times the mass of the Sun. What makes this motion even more extraordinary is that it has real, visible consequences in the cosmos. At such speeds, Zeta Ophiuchi is not moving quietly. Instead, it plows into the thin soup of gas and dust that fills the space between stars. At its velocity, the interaction between its stellar winds and the interstellar medium generates shockwaves, both shocks, that can stretch across light years. The star's speed turns it into something akin to a ship cutting through a cosmic ocean, leaving waves of turbulence behind it. Without its extraordinary velocity, we would not see this spectacular bow shock phenomenon, which has become one of the most iconic images of Zeta Ophiuchi captured by telescopes. Its speed, in other words, doesn't just define its uniqueness, it creates the very spectacle that makes it so fascinating to astronomers. The question of why Zeta Ophiuchi moves so fast is one of the central mysteries of its story, and it ties directly into the idea of it being a runaway star. Ordinary stars are content to remain in their birth clusters or galactic neighborhoods, their motions largely shaped by the overall rotation of the Milky Way. For a star to reach speeds of 24 kilometers per second relative to its surroundings, some powerful force must have acted upon it. In Zeta Ophiuchi's case, the most likely explanation is a violent past, one in which it was once gravitationally bound to another massive star. When that companion ended its life in a cataclysmic supernova, Zeta Ophiuchi was suddenly released, slingshot away from its former orbit at enormous speeds. This violent ejection transformed it from an ordinary cluster member into a galactic wanderer, a fugitive fleeing through space at 50,000 miles per hour. This speed also makes Zeta Ophiuchi's journey uniquely traceable. Astronomers can calculate its past trajectory, working backward from its current position and velocity to estimate where it came from. These galactic breadcrumbs point to star-forming regions where O-type stars like Zeta Ophiuchi are born, suggesting that its current placement in Ophiuchus is only temporary, a stop along its flight path. In the future, it will continue racing across the Milky Way, its speed carrying it ever farther from its origins, until eventually it explodes in its own supernova, leaving behind either a neutron star or a black hole. What's remarkable is that even at such speeds, it will take thousands of years before Zeta Ophiuchi noticeably changes its location in the sky to the naked eye. Human timescales are simply too short to appreciate its movement directly. But with the precision of modern instruments, scientists can measure this drift, and with each passing decade, the data confirm its runaway status. The speed is not slowing. The star remains a fugitive, forever propelled by the violent kick it received millions of years ago. The sheer velocity of Zeta Ophiuchi makes it more than just a star, it makes it a story in motion. It is not static, not fixed, not comfortably seated in the mythological tapestry of Ophiuchus. It is alive with energy, cutting across the galaxy, dragging its violent past behind it like an invisible wake. To gaze at it is not simply to look at a point of light, it is to witness a star in transit, a celestial traveler speeding through the cosmos at a pace that defies ordinary comprehension. When astronomers call Zeta Ophiuchi a runaway star, they're giving it a title reserved only for the most extraordinary stellar wanderers. Most stars are like citizens of a well-ordered city. They stay more or less in the neighborhoods where they were born, bound by the gravitational relationships of their birth clusters and slowly moving along with the general rotation of the galaxy. But runaway stars are the exceptions, the exiles, the fugitives, the wanderers whose velocities betray a violent past. They are stars that, for one reason or another, were kicked out of their stellar families and sent hurtling across the galaxy at speeds far greater than the average. By definition, a runaway star is a star traveling at an unusually high velocity relative to its surroundings, often tens or even hundreds of kilometers per second, fast enough to escape the gravitational pull of the cluster or region where it formed. These stars are essentially cosmic castaways, and their trajectories point away from the nurseries that birthed them. In Zeta Ophiuchi's case, the evidence is clear. Its speed of about 24 kilometers per second relative to its environment is far too great to be explained by normal galactic drift. It does not fit the serene dance of its neighbors. It is moving with purpose, as though it were flung by an unseen hand into its current path across the constellation Ophiuchus. Astronomers classify Zeta Ophiuchi as a runaway star because all the hallmarks are there. Its extraordinary speed, its location away from any dense stellar nursery, and the presence of its spectacular bow shock all confirm that it is not a star simply drifting along. Something happened to eject it, and the traces of that violent event are still visible today. Unlike many other O-type stars, which are usually found nestled in young clusters surrounded by sibling stars, Zeta Ophiuchi lives alone. This isolation is another clue pointing to its runaway nature. A star so massive and so young should not exist in solitude. It should be part of a vibrant, bustling star-forming region. The fact that it is not suggests it was torn away from its birthplace. Runaway stars can come about through two main mechanisms. The first is through gravitational interactions. If a star resides in a dense cluster, close encounters with other massive stars or binary systems can slingshot one or more stars out at tremendous speeds. The second, and perhaps the more dramatic, mechanism is through supernova explosions in binary systems. When two massive stars orbit one another, they form a delicate balance. If one of those stars reaches the end of its life and explodes, the gravitational tether between them snaps instantly. The surviving star is released from orbit, and the momentum it carried flings it outward, sometimes at hundreds of kilometers per second. Zeta Ophiuchi is a prime candidate for this second scenario. Its runaway classification isn't just a label, it's a story written in motion. By tracking its trajectory backward, astronomers believe Zeta Ophiuchi once belonged to a stellar nursery in the Scorpius-Centaurus association, a region rich with young, massive stars. That's where it was likely born, before a catastrophic event, most likely a supernova, sent it hurtling into its current path. Its speed and trajectory match what we would expect from such an ejection, and that's why it has become one of the most iconic examples of a runaway star in our galaxy. What makes Zeta Ophiuchi especially intriguing is that runaway stars are relatively rare, and runaway stars of its magnitude, massive O-type giants, are rarer still. These stars are short-lived, so to see one still intact and racing through the galaxy gives scientists a precious opportunity to study not only the aftermath of violent stellar events but also the effects such stars have on their surroundings as they speed along. In this sense, Zeta Ophiuchi is a living laboratory, a star whose status as a runaway makes it invaluable to astrophysics. It is no exaggeration to say that Zeta Ophiuchi is the poster child for runaway stars. Its bow shock, its high velocity, its isolation, and its suspected supernova origin all weave together into a narrative that explains why astronomers are so confident in its classification. This is not just a star wandering aimlessly, this is a star on a forced journey, carrying with it the legacy of a violent past. Its runaway status turns it from just another bright star in the sky into a cosmic exile, racing onward, unable to return to its home, and destined to one day meet its end in a supernova explosion of its own. As Zeta Ophiuchi barrels through the galaxy at over 24 kilometers per second, it doesn't simply glide through empty space unnoticed. Instead, its immense speed and its ferocious stellar winds create one of the most dramatic and awe-inspiring spectacles astronomers have ever observed. A massive bow shock, a glowing arc of energy that stretches across space like a cosmic shield. This bow shock forms because Zeta Ophiuchi is plowing headlong into the interstellar medium, the thin soup of gas and dust that permeates the Milky Way, so violently that it carves a vast shockwave tens of light-years wide. To understand this, we first have to consider the winds that blow outward from Zeta Ophiuchi. With a surface temperature exceeding 30,000 Kelvin, the star produces intense ultraviolet radiation, and that radiation pushes its outer layers outward at astonishing speeds. The result is a constant gale of stellar winds rushing into space at millions of kilometers per hour. Now imagine those winds colliding with the interstellar medium as Zeta Ophiuchi tears across the galaxy at 50,000 miles per hour. The impact between the outflowing winds and the gas in its path is like an unstoppable force meeting an immovable object, and the result is the creation of a bow shock. Visually, this bow shock resembles a great arc of glowing material curving around the star's forward-facing edge. It's as if Zeta Ophiuchi is carrying a shield before it, warding off the oncoming stream of cosmic matter as it charges ahead. The shock compresses and heats the interstellar gas to the point where it glows, and when observed with infrared telescopes like NASA's Spitzer space telescope, it reveals itself as a vast, luminous structure. The size of this shock is mind-boggling. We're not talking about a few astronomical units or the distance between planets. The arc can stretch across dozens of light-years, dwarfing entire star systems and standing as one of the most impressive manifestations of a star's motion through space. If you were to shrink the universe down to human scale, you might think of Zeta Ophiuchi as a speeding boat moving across a calm lake. The bow of the boat pushes against the water, forcing it into ripples that fan out into the wake behind. The faster the boat moves, the bigger and more dramatic those ripples become. Zeta Ophiuchi is the boat, the interstellar medium is the lake, and its bow shock is the cosmic wave curling in front of it. This analogy helps us grasp what is happening, but in truth, the bow shock of a star is far more complex, involving physics of ionization, heating, and the interplay of stellar winds and interstellar material. Still, the image of a speeding ship cutting through a vast sea is one of the most evocative ways to imagine Zeta Ophiuchi's journey. This bow shock doesn't just look dramatic, it is a profound scientific tool. By studying its structure and brightness, astronomers can learn about both the star and the environment it moves through. The glow we see comes from dust grains that have been heated by the intense ultraviolet light and the violent compression of the shockwave. These glowing grains reveal the density and composition of the surrounding medium, providing insights into the invisible structures of the galaxy. In this way, Zeta Ophiuchi acts like a probe, plowing through space and lighting up the otherwise invisible regions of the interstellar medium. One of the most iconic images of Zeta Ophiuchi comes from Spitzer, which captured the bow shock in exquisite detail. Against the dark background of space, the star sits near the center, with a massive arc of glowing dust sweeping out in front of it. To look at this image is to witness the sheer drama of stellar motion. Most stars are invisible wanderers, their paths leaving no trace. Zeta Ophiuchi, however, leaves scars in space itself, vast, glowing arcs that testify to both its speed and its power. Astronomers estimate that the bow shock extends tens of light-years across, a distance so large that even light, traveling at 300,000 kilometers per second, would take decades to cross it. To appreciate the scale, imagine the solar system dropped inside this shock. Not only would every planet be swallowed, but thousands of solar systems lined up side by side could fit within its arc. The bow shock makes Zeta Ophiuchi not just a star but a sculptor of galactic architecture, carving out shapes in the interstellar medium that will persist long after the star itself is gone. But as grand as this structure is, there is still much astronomers don't fully understand. The physics of bow shocks involves complicated feedback loops between radiation, wind, and matter. In some places, the shock is smooth and steady, while in others it is turbulent and chaotic, almost frothing like whitecaps on a stormy sea. Observing and modeling these structures helps astrophysicists refine their theories about how stars interact with their environments, and Zeta Ophiuchi, with its enormous bow shock, is one of the best laboratories available for studying this cosmic phenomenon. What makes it even more fascinating is that bow shocks are rare to see at this level of clarity. Only the fastest and most energetic stars can produce them, and not all of those shocks are oriented in ways that make them visible to Earth. Zeta Ophiuchi's bow shock, therefore, is both a cosmic rarity and a visual wonder. It transforms what might otherwise be just another bright star into something spectacular, a star wielding a shield of fire and light as it rushes through the darkness. In the grand story of Zeta Ophiuchi, the bow shock is not just a side effect of its speed and power, it is the most visible evidence of its runaway status, the glowing trace that it leaves in the galaxy, and a symbol of how even one star can shape the space around it on scales that defy imagination. When trying to wrap our minds around the vastness of Zeta Ophiuchi's bow shock, with its arc stretching tens of light-years across, it can feel almost impossible to grasp. The distances are too great, the energies too immense, the physics too alien to our everyday experience. That's where analogies come in, and one of the most effective is to compare Zeta Ophiuchi to something far more familiar, a speeding boat cutting through water. Picture yourself standing at the shore of a calm lake on a clear summer day. The surface of the water is smooth, still, unbroken. Then, in the distance, a motorboat roars to life and begins tearing across the surface. Immediately, you notice something happening in front of it. The prow of the boat shoves the water aside, creating a V-shaped wake that stretches outward and trails behind. The faster the boat moves, the larger and more dramatic the waves. Even after the boat has passed, ripples spread out for long minutes, carrying the evidence of its motion across the entire lake. This is the essence of what Zeta Ophiuchi is doing in the vast ocean of the galaxy. In this analogy, the water is the interstellar medium, the thin, nearly invisible gas and dust that fills the space between stars. Zeta Ophiuchi itself is the boat, moving not through water but through that medium, pushed forward by the violent momentum it gained when it was ejected from its original home. And just like the prow of a boat pushes water aside, Zeta Ophiuchi's forward edge pushes against the gas and dust in its path. The difference is that, instead of wooden planks parting water, this star pushes forward with a combination of intense stellar winds and fierce ultraviolet radiation. The interstellar gas doesn't merely ripple like water, it compresses, heats, and glows, forming the enormous bow shock that we can detect with our telescopes. The boat analogy also helps us visualize scale in a way numbers sometimes can't. Imagine zooming in on the front of the boat, where water piles up into a curling wave. That wave is sharp, crisp, and moves along with the boat as it races forward. For Zeta Ophiuchi, the wave is the arc of heated gas and dust, always riding ahead of it, always growing brighter as the star plows forward. Except here's the astonishing part: if you try to compare the wake of a boat to Zeta Ophiuchi's bow shock, the star's version would dwarf entire fleets of oceans. While the wake of a speedboat might stretch a few dozen meters, Zeta Ophiuchi's glowing arc can stretch across tens of light years, vast enough to engulf thousands of entire solar systems. The analogy holds in principle, but the cosmic scale is beyond imagination. Another detail makes the comparison especially vivid. Just as the waves created by a speedboat depend on its speed and the density of the water, the bow shock of Zeta Ophiuchi depends on how fast it moves and how dense the interstellar medium is. If the boat moves slowly, its waves are small and gentle. If it speeds up, the waves grow taller, more forceful, more dramatic. In the same way, if Zeta Ophiuchi were moving slowly or if the interstellar medium around it were especially thin, the bow shock would be faint or perhaps non-existent. But because it is racing along at more than 50,000 miles per hour and colliding with a sufficiently dense region of space, the bow shock blossoms into the enormous, luminous arc that Spitzer and other telescopes have revealed. The analogy also extends to turbulence. Anyone who has watched a boat knows that the wake isn't just a smooth ripple. It churns, froths, and sometimes even creates smaller waves that crash into each other. In space, Zeta Ophiuchi's bow shock shows a similar complexity. Infrared images reveal regions where the shock is smooth and elegant, contrasted with zones of turbulence and irregularity. These are places where the stellar winds and the interstellar medium interact chaotically, producing eddies and swirls that are, in essence, cosmic whitecaps on the surface of an invisible sea. There's a deeper lesson in this analogy too. Just as a boat leaves a mark on a lake long after it has passed, Zeta Ophiuchi leaves a mark on the galaxy. The bow shock stirs up the interstellar medium, compressing it and heating it, and sometimes those compressed regions can become dense enough to collapse under gravity, triggering the birth of new stars. The wake of a speedboat might fade quickly on a summer lake, but the wake of Zeta Ophiuchi may last for millions of years and may even see the creation of entirely new stellar generations. In this way, the boat analogy not only helps us visualize what's happening, it hints at the star's profound influence on the galactic environment. And yet, there's an important caveat. Unlike a boat, which is powered by an engine under human control, Zeta Ophiuchi is not in command of its own journey. It was thrust into motion by cosmic violence, perhaps the death of a companion in a supernova, and now it speeds onward. Relentlessly, unable to slow down or change course. The boat is free to turn, to pause, to dock again at shore. Zeta Ophiuchi has no such choice. Its bow shock is not the product of play or exploration but of exile, a testament to the star's violent history and uncertain future. So, the next time you see a boat skimming across water, picture that on a galactic scale. Replace the lake with the invisible rivers of interstellar gas. Replace the boat with a star 20 times the mass of the sun. Replace the rippling wake with a glowing arc tens of light years across. That image, stretched across the imagination, is what Zeta Ophiuchi is doing right now in the constellation Ophiuchus. It is a speedboat on the ocean of space, forever cutting waves into the galaxy. When astronomers first began to study Zeta Ophiuchi's runaway nature, they knew something dramatic had to be happening in the space around it. A star this massive, this hot, and moving this quickly could not possibly slip quietly through the galaxy. And while visible light telescopes could capture the star itself, they struggled to reveal the full extent of its bow shock because much of the structure is obscured by interstellar dust. It wasn't until NASA's Spitzer space telescope turned its infrared eyes on Zeta Ophiuchi that the true spectacle came into view. A vast, glowing arc of heated dust that looked like a cosmic shield, stretching tens of light-years ahead of the star as it plowed through space. Infrared light was the key to unlocking this hidden structure. Unlike visible light, which is easily blocked or scattered by dust, infrared wavelengths can pierce through those dusty regions, revealing details that would otherwise remain invisible. Spitzer, launched in 2003, was designed specifically to detect such infrared emissions, and when it observed Zeta Ophiuchi, it captured something breathtaking. The star's bow shock shining brilliantly, lit up by the very dust grains that had been heated by the shockwave. The process behind this glow is fascinating. As Zeta Ophiuchi races forward, its stellar winds slam into the interstellar medium, compressing it and generating shockwaves that heat the gas and dust. The ultraviolet radiation pouring off the star then bombards the dust particles caught in the shock, energizing them until they re-emit that energy as infrared light. To our eyes, this process is invisible. But to Spitzer's instruments, tuned precisely to capture such emissions, the region lit up like a beacon. What once looked like an empty stretch of sky around a lonely blue star suddenly revealed itself as a dynamic, glowing structure shaped by the star's violent journey. One of the most iconic images of Zeta Ophiuchi from Spitzer shows the star itself at the center, a bright point of light, with a massive curved arc of glowing dust sweeping across its path. The arc resembles a giant wave curling in front of a ship, except instead of water, it is made of heated interstellar dust grains, and instead of stretching a few dozen meters, it spans light-years. The sheer scale of the bow shock revealed by Spitzer stunned even seasoned astronomers. It was a direct and dramatic visual confirmation of the star's runaway status. The Spitzer image also provided more than just beauty. It provided data. By analyzing the intensity and distribution of the infrared glow, scientists were able to estimate the density of the surrounding interstellar medium and the strength of the star's winds. The bow shock is essentially a map of the collision between Zeta Ophiuchi's outflow and its environment, and Spitzer gave researchers the ability to read that map for the first time in unprecedented detail. In a way, the glowing dust became a cosmic tracer, outlining the invisible interactions that otherwise would have been impossible to measure. Perhaps even more intriguing, the infrared glow showed regions of turbulence and uneven heating, revealing that the bow shock is not a perfectly smooth arc but a complex, shifting structure. Just as the wake of a boat in water can froth and swirl depending on currents and obstacles, Zeta Ophiuchi's bow shock shows hints of instability and chaotic flows. These details gave astrophysicists clues about how stellar winds behave under extreme conditions, and how the interstellar medium itself responds when battered by high-speed intruders like runaway stars. For the general public, though, the Spitzer images became something more than data, they became art. The sight of a massive, glowing arc surrounding a single star resonated deeply with those who saw it. It looked almost like a shield protecting a warrior, or a cosmic wave frozen in time. It transformed Zeta Ophiuchi from a name in a catalogue into a vivid, almost mythological presence, a reminder that the universe is filled not only with stars but with the breathtaking evidence of their interactions with space itself. What Spitzer revealed also raised tantalizing new questions. How stable is this bow shock over time? Does it ripple and change as the star moves, or is it relatively constant? Could it collapse sections of interstellar gas dense enough to spark new star formation in its wake? Observations in the infrared were only the beginning, providing a snapshot of a process that continues to unfold on timescales far beyond a human lifetime. Yet even that single image was enough to cement Zeta Ophiuchi's place as one of the most iconic runaway stars in the galaxy. In the end, the glowing arc of dust captured by Spitzer is more than just a pretty picture. It is a testament to the raw forces at play when a massive star collides with the galaxy around it. It is proof that stars are not isolated points of light but powerful engines capable of reshaping entire regions of space. Without infrared vision, Zeta Ophiuchi's story would have remained incomplete. With it, we see not only the star but the scars it leaves as it races forward, carrying the legacy of its violent past and hinting at the explosive fate that awaits it. Looking at Zeta Ophiuchi today, with its blistering heat, its runaway speed, and its enormous glowing bow shock, is like seeing the aftermath of a cosmic crime scene. The evidence is there, scattered across the sky, a star moving far too quickly for no apparent reason, carving waves through interstellar gas, living in solitude when it should, by all rights, be part of a bustling family of stars in a young cluster. It raises a fundamental question that has haunted astronomers ever since they first identified its unusual speed. Why is Zeta Ophiuchi moving so fast? What could have propelled a star of such immense mass, 20 times the weight of the Sun, into its current flight across the galaxy? Stars do not simply wake up one day and decide to sprint across space. Their motions are determined by gravitational forces, by the environments in which they were born, and by the delicate balance of interactions with nearby stars. For Zeta Ophiuchi to break away so dramatically, some extraordinary event must have shattered that balance. Its past is wrapped in mystery, and every detail astronomers can observe today serves as a clue pointing backward toward that defining moment. The first clue comes from its sheer isolation. A star as massive as Zeta Ophiuchi is rare, and such stars are almost always found in clusters or associations. Groups of young, hot stars form together in vast clouds of gas and dust. Yet Zeta Ophiuchi sits alone, far from the nurseries where it should be. This suggests it didn't form where we see it today. Instead, it was flung here, cast out from its birthplace like a stone from a sling. Its current position, traced back through models of its trajectory, points toward the Scorpius-Centaurus association, a rich region of massive stars that could easily have produced a system like Zeta Ophiuchi. The second clue lies in its runaway speed itself. The velocity is not random, it's too high to be explained by ordinary galactic drift, yet not so extreme as to suggest a supermassive black hole encounter or some exotic gravitational slingshot. Its speed is perfectly consistent with what astronomers expect when a binary star system is disrupted by one of its members exploding as a supernova. In such a system, two massive stars orbit each other, bound by gravity. When one reaches the end of its life and detonates, the explosion not only destroys the star but also suddenly removes the gravitational anchor that kept its companion tethered. The surviving star, in this case, Zeta Ophiuchi, is hurled outward at the same speed it once orbited, now freed and carrying its momentum through space as a runaway. There is, however, a third and even subtler clue, the bow shock itself. Zeta Ophiuchi's winds and radiation are undeniably intense, but the dramatic arc stretching ahead of it depends on the fact that it is moving through space at such a high speed. Without that runaway motion, there would be no glowing shield, no colossal wave of dust curling in front of it. The bow shock is both a consequence of its present and a signature of its past. It is the ongoing evidence of that ancient ejection, written not in numbers on a chalkboard but in the very structure of interstellar gas. All of these clues converge on the same mystery. Zeta Ophiuchi is not where it belongs, and the reason lies in an event so violent that it changed the course of the star's existence forever. What astronomers see now is the aftermath, but the cause, the supernova, the vanished companion, the moment of ejection, happened millions of years ago. In this sense, observing Zeta Ophiuchi today is like walking into the middle of a story whose opening chapter has been lost. We can read the characters, we can follow the plot lines, but the inciting incident remains hidden in time, waiting to be pieced together from the fragments of evidence left scattered in the galaxy. And so, the star becomes more than just a runaway. It becomes a mystery. A question mark written across the night sky. Its speed demands an explanation, its isolation hints at exile, and its bow shock testifies to a collision with its surroundings. Each observation adds weight to the theory of a violent past, yet each also deepens the sense that Zeta Ophiuchi is keeping secrets. The very fact that we must ask why it is moving so fast is a reminder that the universe does not always present us with easy answers. Sometimes, we are left to reconstruct the crime scene from what little evidence remains, knowing that the true moment of violence is lost in the depths of cosmic history. The story of Zeta Ophiuchi's runaway speed begins to take shape when we imagine it not as a solitary giant, but as one half of a pair. For much of its early life, astronomers believe, Zeta Ophiuchi was not alone. It was bound in a binary system, orbiting in tandem with another massive star. Binary systems are incredibly common in the galaxy, especially among the most massive stars, and these stellar partnerships can last for millions of years. Each star tugs on the other with its immense gravity, locking them in an elegant, sometimes precarious dance. Now picture Zeta Ophiuchi circling such a companion. Both were giants, both far larger and more short-lived than our Sun, and both burning through their nuclear fuel at a furious pace. But in the balance of that system, one of the stars was destined to reach the end first. When its companion's core could no longer support the crushing weight of its outer layers, the star's life ended in one of the most violent events the universe has to offer, a supernova. A supernova is more than just an explosion. It is a cataclysm so powerful that, in a matter of seconds, the dying star can outshine an entire galaxy. The blast rips apart the outer layers, hurls matter into space at incredible speeds, and leaves behind either a neutron star or a black hole. But in a binary system, the effects of a supernova extend far beyond the star that dies. In that moment of violent release, the delicate gravitational balance between the two stars is shattered. For Zeta Ophiuchi, this was the turning point. Before the explosion, its orbit around its companion was stable, even if it meant it was whipping around at tens of kilometers per second. But when the companion star blew itself apart, the mass anchoring Zeta Ophiuchi in orbit was suddenly gone. With the tether cut, Zeta Ophiuchi didn't stop moving. It simply kept going, carrying with it the same velocity it had possessed as it circled its partner. What had once been orbital motion was transformed into a straight-line flight path. The result, a star flung out of its home, ejected into the galaxy as a runaway. This explanation fits the evidence perfectly. Zeta Ophiuchi's current speed, about 24 kilometers per second relative to its surroundings, is exactly the kind of velocity astronomers would expect if it had once been bound to a massive companion that died in a supernova. It also explains its isolation. Stars like Zeta Ophiuchi don't form alone in quiet patches of space. They are born in crowded nurseries surrounded by siblings. Its current position, far from such regions, makes sense only if it was cast out millions of years ago. The supernova explanation also sheds light on the shape of Zeta Ophiuchi's destiny. Having lost its partner, it now races alone, carrying not just its own story but the memory of that cataclysmic event. Somewhere, perhaps millions of years in the past, its companion star exploded, scattering heavy elements across space, enriching the galaxy with the building blocks of planets and life, and leaving Zeta Ophiuchi to wander onward. The bow shock it creates today is not just the result of its motion, it is a continuing consequence of that supernova event, a signature of its forced exile. Astronomers have searched for traces of that missing companion. In theory, it should have left behind either a neutron star or a black hole. Yet no such remnant has been clearly identified in the region from which Zeta Ophiuchi likely came. This absence adds a layer of mystery to the narrative. Did the companion collapse into a black hole so faint it remains invisible to our instruments? Or has the remnant drifted away on its own path, as elusive as Zeta Ophiuchi is dramatic? The questions remain open, but the broad strokes of the theory are clear. Zeta Ophiuchi is running today because its partner died in a violent explosion. The supernova explanation transforms the way we see this star. It is not merely a wanderer, it is a survivor. It has endured one of the most catastrophic events in the cosmos, and in doing so, it was given both freedom and exile. Its runaway journey is not self-chosen but imposed upon it by the death throes of another star. In the silence of the night sky, Zeta Ophiuchi carries with it the echoes of a supernova blast that took place long before human beings even existed to wonder about it. The tale of Zeta Ophiuchi becomes even more intriguing when we pause to consider not just the star itself, but the ghost of the one that is no longer there, the missing companion. For if the leading theory is correct, then Zeta Ophiuchi did not begin its journey through the galaxy alone. It once shared its life with another massive star, a stellar sibling locked in a binary embrace. Together they orbited their common center of gravity, their mutual pull keeping them bound. But then came the explosion, the cosmic detonation that tore one apart and sent the other, Zeta Ophiuchi, hurtling into the void. And yet, when astronomers peer into the depths of space searching for the remnant of that long-dead partner, they see nothing definitive. The companion is gone, vanished as though it never existed. This absence is not only a puzzle, but also one of the most haunting elements of Zeta Ophiuchi's story. It is as though the star carries the shadow of a ghost beside it, an invisible memory of the one that altered its fate forever. The likely explanation is that the missing star collapsed into either a neutron star or a black hole. Both of these remnants are notoriously difficult to detect unless conditions are just right. A neutron star can be spotted if it spins rapidly and emits beams of radiation that sweep across Earth like a cosmic lighthouse. In that case, it becomes visible as a pulsar. A black hole might betray itself by feeding on nearby matter, releasing X-rays in the process. But if the remnant of Zeta Ophiuchi's companion is quiet, if it neither spins in such a way to beam at us, nor feeds on material that would make it glow, then it would slip almost invisibly into the galactic background. This invisibility makes the missing companion feel like an unsolved riddle. Somewhere out there, hidden in the Milky Way, is the corpse of the star that once shared Zeta Ophiuchi's orbit. It may still be moving, perhaps even on a trajectory as dramatic as Zeta Ophiuchi's own, cast away by the force of the blast. Its identity is erased, but its influence is undeniable. Without that explosion, Zeta Ophiuchi would not be a runaway. Without that death, there would be no bow shock slicing across the interstellar medium, no mystery for astronomers to puzzle over. The absence of the companion is, paradoxically, the most tangible clue we have to explain the runaway's existence. And yet, the lack of direct evidence leaves space for imagination. Did the companion collapse into a black hole that now wanders invisibly, a silent predator in the dark? Could it have been a neutron star that has drifted too far for us to notice, spinning quietly in the shadows of the galaxy? Or, in a more dramatic twist, could the explosion have been so complete, so thorough, that little remained to leave a trace at all? Whatever the answer, the missing companion is more than just a detail in Zeta Ophiuchi's past. It is the catalyst that shaped its destiny. That single supernova altered the trajectory of a star 20 times the mass of the Sun, flinging it out of its birthplace and sending it into exile. It transformed Zeta Ophiuchi from an ordinary member of a binary system into one of the most remarkable runaway stars known to science. Without the missing companion's final sacrifice, Zeta Ophiuchi might still be quietly orbiting another massive star, its life hidden away in a stellar nursery. Instead, it is racing across the galaxy, carrying with it the story of a violent ending and a lonely survival. There is something profoundly poetic about this. Zeta Ophiuchi shines brightly in our sky, not because of what it is alone, but because of what it has lost. Its destiny is not self-determined, but bound to the ghost of a companion we cannot see. The mystery of that vanished star lingers in every image of its bow shock, in every measurement of its runaway speed, in every speculation about its future. In a very real sense, Zeta Ophiuchi is a monument to that lost partner, a living reminder that even in death, a star can shape the cosmos for millions of years to come. When we think about stars, we often imagine them as fixed points in the sky, unchanging and eternal. In reality, stars are not still at all. They orbit around the center of the Milky Way, carried along by the gravitational currents of the galaxy. Most stars, including our Sun, drift with relatively predictable motions, like orderly dancers moving together in a grand cosmic waltz. But Zeta Ophiuchi breaks from that rhythm. It is not drifting quietly along with the rest. It is fleeing, fast and restless, a true galactic escapee. Calling Zeta Ophiuchi an interstellar fugitive is not just poetic language, it is a reflection of its real status. This star was not born where we see it today. Its spectral properties, its size, and its age all point to an origin in one of the nearby massive star-forming regions, likely the Scorpius-Centaurus association. That region is brimming with other massive, young stars, many of them still in loose clusters, surrounded by the remnants of the clouds that gave birth to them. Zeta Ophiuchi fits that family perfectly, except for one crucial difference: it is no longer there. Something tore it away from its birthplace, and now it is racing across the galaxy, alone. The analogy of a fugitive fits for another reason as well. Like a prisoner breaking free of confinement, Zeta Ophiuchi has escaped the gravitational pull of its original home. Its speed, about 24 kilometers per second relative to its environment, was enough to eject it from the cluster where it was born. Imagine a stone flung from a sling. Once released, it no longer circles but flies in a straight path outward. That is Zeta Ophiuchi, carrying the memory of its violent past as it streaks away from the family it once belonged to. Astronomers can even trace its trajectory backward through space, like detectives retracing the steps of a fleeing suspect. Doing so reveals that millions of years ago, Zeta Ophiuchi likely passed through regions of the sky filled with other hot, young stars, places where it almost certainly originated. Its flight path doesn't meander randomly. It points back toward the neighborhoods of star formation that gave it life, and its current position relative to those regions is exactly what one would expect for a star ejected at high speed millions of years ago. To picture this more vividly, imagine the Scorpius-Centaurus association as a bustling city filled with bright, massive stars, all relatively close together. Now imagine that one catastrophic event, a supernova, blows apart that peaceful arrangement. In the chaos, one of the brightest citizens of that city, Zeta Ophiuchi, is hurled out into the countryside. Today, we see it miles away from its birthplace, traveling as if it were an exile. It carries none of the companionship of its siblings, none of the familiar surroundings of its star-forming nursery. It is a lone traveler, leaving behind the place that forged it. This exile status makes Zeta Ophiuchi different from the vast majority of stars we study. Our Sun, for example, has lived in the same broad region of the galaxy for billions of years. It was born here, and here it remains, orbiting stably around the galactic center. Zeta Ophiuchi, by contrast, is a nomad, cast out and set adrift. Its motion through space is not just ordinary galactic orbiting, it is the trajectory of a star that has been ejected, a fugitive racing with a speed and direction that mark it as an outlier. What makes this even more striking is that Zeta Ophiuchi is not unique in this status. Astronomers have found other runaway stars, other fugitives fleeing their homes at unusual speeds. But Zeta Ophiuchi is one of the most dramatic examples, not only because of its velocity but also because of its sheer mass and energy. A small star ejected from a cluster might wander quietly, unnoticed. But a giant like Zeta Ophiuchi cannot help but announce its presence. It carves a bow shock through the interstellar medium. It lights up dust with its ultraviolet radiation. It leaves trails that make its exile visible across the electromagnetic spectrum. There's something profoundly human about the image of Zeta Ophiuchi as a fugitive. It is a reminder that even in the vastness of space, exile and loneliness are real fates. It did not choose this path, but it was forced upon it by the violent death of a companion. Now it continues onward, far from its birthplace, destined never to return. In its brightness and speed, it is both a survivor and an outcast, its entire life story rewritten in the moment of that long-ago explosion. In the end, calling Zeta Ophiuchi an interstellar fugitive captures both the science and the drama. It explains why it is where it is, why it moves the way it does, and why its bow shock slices through space like a shield on the run. It is a star defined not by where it was born, but by what it escaped. The violence of Zeta Ophiuchi's existence is not only written in its speed or its lonely exile, it is also imprinted directly onto the fabric of the space it passes through. This colossal star is more than just a bright point of light. It is an engine of raw energy, continuously blasting its surroundings with radiation and matter. Its surface temperature, tens of thousands of degrees hotter than our Sun, ensures that it floods its environment with ultraviolet radiation, and its stellar winds, streams of charged particles hurled outward at incredible velocities, are among the strongest known. Together, these forces carve into the interstellar medium, reshaping it in ways that ripple across light years. To grasp the scale of these winds, we must remember that stars like Zeta Ophiuchi are not calm spheres quietly burning fuel. They are dynamic furnaces with outer layers so unstable that matter is continually stripped away. In Zeta Ophiuchi's case, the flow of particles surging outward is so powerful that it pushes into the surrounding gas and dust, creating cavities, literal bubbles, in the interstellar medium. These bubbles are not empty, but they are cleared-out regions where the density of matter is dramatically reduced, sculpted by the unrelenting force of the star's outflow. Think of it as a storm system moving across the galaxy. Just as hurricane winds on Earth can uproot trees, scatter debris, and carve new landscapes, the stellar winds from Zeta Ophiuchi plow into the interstellar medium, compressing some regions and dispersing others. The result is turbulence on a galactic scale. Where there was once a uniform cloud of gas, there is now a complex web of shock fronts, compressed shells, and heated voids. In some places, this disruption may even trigger the birth of new stars. Compressed gas can collapse under its own gravity, forming stellar nurseries in the very wake of destruction left by Zeta Ophiuchi's winds. And then there is the radiation itself. The ultraviolet light streaming from Zeta Ophiuchi is intense enough to ionize hydrogen atoms, stripping electrons from protons in the gas around it. This ionization creates glowing nebulae, regions where interstellar gas shines because of the relentless energy bombarding it. While the bow shock is the most visible testament to the star's motion, these ionized regions are evidence of how profoundly its radiation changes the character of the space it inhabits. Zeta Ophiuchi does not merely pass through the galaxy, it alters the state of the very medium it touches. The combination of radiation and winds also ensures that Zeta Ophiuchi is continuously losing mass. Over the course of its short life, it will shed enormous amounts of material into space. This is a key contribution to the galactic ecosystem. Heavy elements forged deep in the star's core are carried outward, enriching the interstellar medium with ingredients for future generations of stars and planets. In this way, even before Zeta Ophiuchi ends its life in a supernova, it is already participating in the cycle of creation and destruction that drives galactic evolution. Astronomers have long recognized that stars like Zeta Ophiuchi are architects of their environments. The bubbles they carve, the winds they unleash, the radiation they pour out, these are not small or localized effects. They reshape the interstellar landscape across tens or even hundreds of light-years. Zeta Ophiuchi may be a fugitive, but it is not a silent one. Everywhere it goes, it leaves scars and signatures behind, as if announcing its presence to the cosmos in the most dramatic way possible. The irony is that this shaping of space comes at a cost to the star itself. The same winds that carve bubbles are also stripping Zeta Ophiuchi of its mass, hastening its eventual demise. Every particle it hurls outward brings it one step closer to the inevitable collapse that awaits it in a few million years. It is a cycle of giving and taking. The star sacrifices itself piece by piece, and in doing so, it enriches the galaxy, stirring the gas that may one day give rise to new stellar generations. In this sense, Zeta Ophiuchi embodies one of the deepest truths of astrophysics, that stars are not isolated islands, but active participants in shaping the universe. Its extreme radiation and stellar winds are both destructive and creative. They tear apart existing structures but also set the stage for new beginnings. As it races through the galaxy, Zeta Ophiuchi is like a cosmic sculptor, its chisel made of radiation, its hammer the gale-force winds of its unstable outer layers. The bubbles it leaves behind are not empty voids, but living testaments to the violence and generosity of a massive star in its prime. Despite its brilliance and its power, Zeta Ophiuchi is a star racing against time. Unlike our Sun, which measures its lifespan in billions of years, this massive runaway has only a fleeting existence by cosmic standards. Its size, around 20 times the mass of the Sun, comes with a cost. The more massive a star is, the faster it burns through its nuclear fuel. Zeta Ophiuchi blazes so intensely that it has only a few million years left to live before its fiery life comes to an explosive conclusion. This is one of the great paradoxes of stellar evolution. A larger star contains vastly more fuel than a smaller one, but it doesn't pace itself. Instead, it burns with such ferocity that the reserves of hydrogen in its core are consumed at breakneck speed. Zeta Ophiuchi's surface temperature, more than 30,000 Kelvin, speaks to the intensity of the processes within. Every second, it is fusing immense quantities of hydrogen into helium, releasing energy on a scale almost unimaginable. For us, that means light and radiation that can travel hundreds of light-years. For the star itself, it means that its internal clock is ticking faster than it would for a calmer, smaller star. Astronomers estimate that stars like Zeta Ophiuchi live for perhaps 8 to 10 million years in total, a tiny fraction of the Sun's expected 10 billion-year lifespan. To put this in perspective, if the Sun's life were a human's 80 years, then Zeta Ophiuchi would be like a person who lives for less than a single year. It shines brilliantly, but it does so with a ferocity that guarantees an early death. Even now, as we study it from Earth, it is already well into its short life cycle. The runaway star we see cutting across the galaxy is closer to its end than its beginning. This short lifespan also raises an important point. Zeta Ophiuchi has already lived through extraordinary events in just a few million years. It was born in a stellar nursery, paired in a binary system, experienced the violent death of its companion in a supernova, and has since been cast out as a runaway carving a bow shock across the interstellar medium. That is more drama in a few million years than the Sun will experience in its entire long and steady life. The sheer pace of its evolution underscores how quickly massive stars live, burn, and die. The limited lifespan of Zeta Ophiuchi also foreshadows its fate. Every star's end is determined by its mass, and there is no question about what awaits a star this large. When its hydrogen fuel is exhausted, it will move on to burning helium, then progressively heavier elements. But eventually, the chain will end when it begins producing iron in its core, an element that cannot generate energy through fusion. At that moment, the balance between gravity pulling inward and fusion pushing outward will collapse. The core will implode under its own weight, and Zeta Ophiuchi will die in the same way its companion did, in a spectacular supernova explosion. It is sobering to realize that this cataclysm could come within just a few million years, a blink of an eye in cosmic history. Though we are unlikely to witness its death within human timescales, the inevitability of its fate adds weight to every observation we make of it today. We are not just studying a star, we are watching a brief chapter in the life of a cosmic titan, aware that the book will end far sooner than it will for our sun. And so, Zeta Ophiuchi's short lifespan is part of what makes it so mysterious and captivating. It is a reminder that brilliance often comes at the cost of longevity. The same forces that make it a beacon in the sky, the immense mass, the blistering heat, the runaway speed, are the very reasons it will not last. It is a candle burning not at one end, but at both, pouring its energy into the cosmos and racing toward an inevitable, violent conclusion. The fate of Zeta Ophiuchi is sealed, and that fate is nothing less than spectacular. When its time runs out, and the final reserves of nuclear fuel in its core are exhausted, it will not fade quietly into the night like smaller stars do. It will go out with one of the most violent displays the universe has to offer, a supernova. For a star as massive as Zeta Ophiuchi, this final act will shake the very fabric of its surrounding region of the galaxy, leaving a legacy written in glowing nebulae, shockwaves, and perhaps even a collapsed remnant like a neutron star or a black hole. To understand the scale of what awaits Zeta Ophiuchi, imagine a blast so bright it could rival an entire galaxy for days or even weeks. When the star's iron core collapses under the crushing weight of gravity, the implosion will be nearly instantaneous. Then, as the core rebounds, an outward explosion will tear through the outer layers, ejecting them into space at a fraction of the speed of light. In that moment, Zeta Ophiuchi could release more energy than our Sun will emit in its entire 10 billion year life. This is the destiny of stars that burn so quickly and live so violently, a finale that is as dramatic as their lives. If such an explosion were to happen within human history, the sight from Earth would be unforgettable. At just over 360 light-years away, Zeta Ophiuchi is relatively close by cosmic standards. Its supernova would likely be visible even during the day, a blazing new point of light dominating the sky for weeks. For ancient civilizations, events like this inspired awe and fear, often interpreted as omens or messages from the heavens. If humanity is still watching when Zeta Ophiuchi explodes, the night sky will be altered in a way no one alive could ignore. But beyond its visual spectacle, the supernova's impact on its surroundings would be profound. The shockwave from the blast would sweep across interstellar space, compressing and heating clouds of gas in its path. This compression could serve as the spark for new star formation, making Zeta Ophiuchi's death the catalyst for the birth of future stellar generations. The elements it forged in its core, carbon, oxygen, silicon, and even iron, would be hurled into space, enriching the galaxy with the raw materials for planets, moons, and potentially life itself. This is the paradox of stellar death. It is an ending, but also a beginning, recycling matter so that the galaxy can continue evolving. Closer to home, astronomers would also be curious about the radiation unleashed by such a blast. Supernovae flood space with high-energy particles and light, including X-rays and gamma rays. While Zeta Ophiuchi is far enough away that Earth itself would not be directly endangered by its explosion, its radiation would still ripple through space, possibly influencing nearby interstellar structures and cosmic rays that eventually reach our solar system. In this way, even from hundreds of light-years away, the death of Zeta Ophiuchi would touch us, a subtle reminder of how interconnected everything in the galaxy truly is. The aftermath would be equally dramatic. The ejected material would expand into a glowing supernova remnant, a vast, colorful cloud stretching across light-years. Over tens of thousands of years, this remnant would continue to expand and evolve, like the famous Crab Nebula we see today from another star's explosion nearly 1,000 years ago. Inside the remnant, at the very center, would lie the collapsed core of Zeta Ophiuchi, perhaps a neutron star spinning rapidly and emitting beams of radiation, or perhaps a black hole, silently bending spacetime itself. Which of these remnants it leaves behind depends on the details of its mass when the collapse happens. But either way, it would be one of the most exotic objects in the universe. In speculating about Zeta Ophiuchi's future explosion, we are forced to confront one of the most profound truths of astrophysics. Death is not the end for stars like this. Instead, it is a transformation. When Zeta Ophiuchi dies, it will seed its corner of the galaxy with heavy elements, carve out new structures in the interstellar medium, and perhaps even set the stage for new stars to ignite. Its bow shock, its runaway speed, and its turbulent past will all be swept away in the brilliance of its final act. What remains will be both a grave marker and a cradle, a reminder that even in destruction, the cosmos is endlessly creative. For now, though, the countdown continues. Whether its explosion comes in 2 million years or 3, the universe is patient, and the stage is already set. Zeta Ophiuchi is a ticking time bomb, and when it finally goes off, it will leave behind a legacy that will shape its surroundings for millions of years. It is not just a runaway star, it is a runaway star with an explosive destiny, one that will one day make its mark on the galaxy in the brightest possible way. When we speak of Zeta Ophiuchi's ultimate fate as a supernova, the vision is already awe-inspiring, a stellar detonation so powerful it could outshine entire galaxies for weeks. But there is an even darker, more dangerous possibility lurking in its future, one that strikes fear and fascination into the hearts of astronomers: the chance that its death could unleash a gamma-ray burst. These are the most energetic explosions known in the universe, focused not in all directions, but in narrow, deadly beams that can travel across thousands of light-years. If Zeta Ophiuchi were to produce such a burst, and if by some cosmic coincidence Earth lay in its direct line of fire, the effects could be devastating. Gamma-ray bursts, or GRBs, are like the universe's sniper shots. Unlike a supernova's energy, which radiates outward in a vast expanding shell, GRBs channel their energy into tightly collimated jets that shoot out along the star's poles. These jets carry more destructive power in a few seconds than our Sun will release in its entire lifetime. For planets caught in their path, the consequences could include the stripping of atmospheres, the destruction of protective ozone layers, and a flood of radiation that would sterilize the surface. On Earth, a nearby GRB aligned with us could trigger mass extinctions, altering life as we know it. The question, then, is whether Zeta Ophiuchi could create such a burst. The star has the right qualities. It is massive, it is hot, and it is spinning. GRBs are thought to be the result of massive stars collapsing into black holes while still maintaining rapid rotation. This rotation allows the collapsing core to funnel energy into those deadly polar jets. With Zeta Ophiuchi's mass, around 20 times that of the Sun, it is certainly in the category of stars capable of such an event. If it collapses into a black hole rather than a neutron star, the odds of a GRB increase further. Fortunately for us, even though Zeta Ophiuchi is relatively close in cosmic terms, only about 366 light-years away, astronomers believe the danger to Earth is low. The key lies in alignment. Gamma-ray bursts are directional, and the Earth would have to be positioned almost perfectly along one of Zeta Ophiuchi's polar axes to suffer the brunt of its blast. If we are not in that line of fire, the radiation from its supernova will still reach us, but it would be dispersed enough across space to cause no real harm. And while Zeta Ophiuchi's spin is significant, there is no strong evidence yet that its rotation is aligned in such a way that Earth would be at risk. Still, the possibility is chilling. Scientists studying GRBs have speculated that such events may have played a role in Earth's past mass extinctions, perhaps stripping away atmospheres and altering climates in ways that reshape the course of evolution. If Zeta Ophiuchi were to generate a GRB, the sheer proximity of 366 light-years would make it one of the most dangerous stars in our celestial neighborhood. Even though the probability of alignment is slim, the potential consequences are so catastrophic that it remains a subject of serious study. Beyond the risk, though, the very concept of a GRB adds another layer of mystery and drama to Zeta Ophiuchi's story. Here is a star already marked by exile, already carrying the legacy of a violent past, already carving waves of chaos through the galaxy as it runs. And yet, its end may not be merely bright, it could be deadly, capable of launching invisible beams of destruction across vast distances. For a star so far away to still hold the power to threaten Earth is a reminder of just how fragile our place in the cosmos truly is. The thought also connects us more deeply to the cycles of life and death in the galaxy. If Zeta Ophiuchi were to unleash a gamma-ray burst, it would be terrifying from the perspective of life on Earth. But on a broader scale, such bursts are part of how the universe distributes energy, reshapes galaxies, and influences the environments where stars and planets are born. What we see as destructive is, at the cosmic level, simply another manifestation of change. For now, we can take comfort in the odds. Astronomers calculate that the Earth is not likely in the direct line of danger from Zeta Ophiuchi's eventual death throes. But even if we are safe from its beams, the possibility adds a note of suspense to its story. This runaway star is not just a fugitive racing through the galaxy, it is a potential cosmic weapon, carrying within it the seeds of an explosion that could reshape its surroundings and possibly alter life itself if fate aligned just so. When we turn our gaze to Zeta Ophiuchi, we don't just see a runaway star. We see it framed against the backdrop of a constellation with an ancient history and mythological weight. That constellation is Ophiuchus, the serpent-bearer, one of the more enigmatic figures drawn into the tapestry of the night sky by human imagination. While modern astronomy places Zeta Ophiuchi within the boundaries of Ophiuchus, people thousands of years ago saw these stars and wove them into stories that reflected their fears, hopes, and understanding of the universe. In this way, Zeta Ophiuchi is not only an astrophysical marvel but also part of a cultural lineage stretching back into antiquity. Ophiuchus is depicted as a man grasping a great serpent, often drawn across the sky as two long lines of stars representing the snake's body. This association of a human figure with a serpent taps into a deep symbolic current found in many cultures, the serpent as a creature of wisdom, healing, danger, and transformation. In Greek mythology, Ophiuchus is often linked to Asclepius, the god of medicine. According to legend, Asclepius learned the secrets of healing from observing serpents and was so skilled in medicine that he could even bring the dead back to life. Such a gift, however, angered Zeus, who feared that the natural order of life and death was being upset. To strike a balance, Zeus placed Asclepius in the stars as Ophiuchus, immortalizing his legacy but also curbing his power. This mythic backdrop resonates beautifully with Zeta Ophiuchi's own story. The star itself has lived a life of disruption, cast out from its birthplace, severed from its companion, now racing through space leaving shockwaves in its path. Just as Asclepius tampered with the natural order, Zeta Ophiuchi's existence seems to challenge the ordinary life cycles of stars. It is as though the myths and the astrophysics intertwine, giving the constellation an uncanny symmetry between human storytelling and cosmic reality. Interestingly, Ophiuchus is sometimes referred to as the forgotten zodiac sign. While the Sun actually passes through Ophiuchus between late November and mid-December, traditional astrology left it out of the zodiac's 12 signs. In that sense, Ophiuchus has always been a bit of an outsider, an overlooked player in the grand stage of the sky. How fitting, then, that Zeta Ophiuchi, a runaway star and a cosmic outsider, belongs to this very constellation. The parallels practically write themselves, a constellation associated with healing, hidden knowledge, and being overlooked, and within it, a star defined by mystery, displacement, and a destiny unlike most others. Beyond the myths, Ophiuchus was also recognized by many other cultures. Ancient Egyptians saw connections between its stars and their own deities, while Babylonians and Sumerians gave different interpretations to the serpent and the man. In many traditions, serpents were symbols of both life and death, poison and cure, a duality that mirrors the star's own fate. Zeta Ophiuchi blazes with life-giving energy now, but its future holds a death so violent it will transform its surroundings. Like the serpent of myth, it carries both danger and creation within itself. Even for modern stargazers, there's something poetic about seeing Zeta Ophiuchi nestled in Ophiuchus. We know now that it is about 366 light-years away, a runaway star shaped by a supernova, plowing through the galaxy at blistering speeds. And yet, when we step outside on a dark night, what we see is what humans have seen for thousands of years. A faint star among others, forming part of a great celestial figure whose arms clutch a serpent. Our scientific understanding and our mythological imagination are not opposed but complementary. One tells us what Zeta Ophiuchi is, the other gives it meaning in a broader human story. In this way, the cultural context of Ophiuchus enriches our appreciation of Zeta Ophiuchi. It reminds us that our relationship with the stars is not just analytical but also emotional and symbolic. For all its astrophysical strangeness, Zeta Ophiuchi is also part of a narrative that stretches across time, uniting ancient storytellers with modern astronomers in a shared act of wonder. Zeta Ophiuchi is not just an astronomical curiosity or a mythic fixture in the night sky, it is also a laboratory in motion, a natural experiment unfolding in real time. Runaway stars like this one give astronomers an extraordinary opportunity to study questions that would otherwise remain cloaked in theory or hidden in distant, inaccessible corners of the galaxy. When we observe Zeta Ophiuchi, we are not only admiring a strange and beautiful star, we are also gathering data that helps unravel the life cycles of the most massive stars, the physics of supernovae, and the turbulent dynamics of our Milky Way. One of the key reasons Zeta Ophiuchi is so important to science is because of its status as a runaway. Most stars remain tied to the gravitational neighborhoods where they were born, clusters of siblings drifting together through the galaxy. But when a star is cast out, as Zeta Ophiuchi has been, it provides a direct clue to the violent forces that shape stellar evolution. Its very speed is evidence of a dramatic event in its past, almost certainly tied to the explosion of its companion. This gives scientists a way to connect theory with reality. They can study its motion, trace it backward through space, and confirm whether the models of supernova kicks and binary disruptions match what we see in the sky. Each runaway star like Zeta Ophiuchi becomes a test case, a puzzle piece that validates or challenges our understanding of how massive stars live and die. Beyond its motion, the star's powerful winds and bow shock also shed light on how massive stars interact with their environments. These winds are not gentle breezes but torrents of high-energy particles blasting into surrounding gas and dust. By observing Zeta Ophiuchi's bow shock, the glowing arc where its winds collide with interstellar matter, scientists gain insight into the physics of shockwaves, turbulence, and energy transfer in space. These processes are not minor. They help regulate how galaxies evolve, stirring up the interstellar medium, redistributing heavy elements, and even sparking the birth of new stars. In this sense, Zeta Ophiuchi is a vivid reminder that stars do not live in isolation but play an active role in shaping their cosmic neighborhoods. Its classification as an O-type star is another reason it is scientifically precious. O-type stars are rare, short-lived, and difficult to study precisely because they burn out so quickly. That makes each one a rare gem for astronomers trying to piece together the early stages of stellar evolution. Zeta Ophiuchi gives scientists a front-row seat to the midlife of such a star, allowing them to study its structure, its radiation output, and its eventual trajectory toward collapse. What's more, because of its relative closeness to Earth, just 366 light-years away, it is one of the best-studied examples of its type. For astrophysicists who model stellar atmospheres, nuclear fusion rates, and stellar winds, Zeta Ophiuchi provides real data to anchor their equations. Another layer of its importance lies in the connection to supernova dynamics. If Zeta Ophiuchi was indeed ejected from its binary system after its partner exploded, then it carries in its trajectory the fingerprints of that explosion. By carefully measuring its speed, direction, and position in the galaxy, astronomers can reconstruct the energy and violence of that long-ago supernova. This isn't just idle curiosity. Understanding these dynamics helps scientists refine models of how supernovae impart momentum to their surroundings, how binary systems are disrupted, and how the galaxy becomes seeded with the heavy elements that supernovae produce. Every clue Zeta Ophiuchi provides is a small but crucial piece of the bigger picture of galactic evolution. And then there is the question of its future. Because Zeta Ophiuchi itself will end in a supernova, it provides an ongoing case study of what happens in the lead-up to such explosions. Scientists can track its changes over time, its luminosity, its winds, its spectral signatures, to better understand the warning signs of a star approaching its death. This knowledge is not just theoretical, it can be applied to other stars on the brink of collapse, helping astronomers predict which stars may go supernova next and what the consequences will be for their local environments. Runaway stars like Zeta Ophiuchi also play a role in galactic archaeology. By tracing their motions backward, astronomers can identify their birthplaces, which often leads to new discoveries about the clusters and star-forming regions they once inhabited. In this way, Zeta Ophiuchi helps us reconstruct the Milky Way's past, piece by piece, like detectives unraveling the history of a crime scene. It tells us not only about itself but about the cosmic neighborhood that gave birth to it and the violent processes that expelled it. Ultimately, the scientific importance of Zeta Ophiuchi lies in its ability to connect so many threads at once: stellar evolution, supernova dynamics, galactic ecology, and the physics of shockwaves and stellar winds. It is a single star, but in its motion, its radiation, and its destiny, it encapsulates the drama of the universe on scales far larger than itself. Studying it is not just about learning the story of one runaway. It's about understanding how the galaxy itself grows, evolves, and recycles its matter. That is why astronomers continue to train their telescopes on it, why models are refined in its name, and why this runaway fugitive of the stars has become such a central figure in our exploration of cosmic mysteries. One of the most fascinating things about Zeta Ophiuchi is that its story doesn't just unfold in the present, it can also be rewound. Astronomers, like cosmic detectives, use the tools of galactic archaeology to trace its trajectory backward through space, asking a simple but profound question: where did this runaway star come from? Every star has an origin, and for Zeta Ophiuchi, its birthplace may hold vital clues to the mystery of its violent past, its vanished companion, and the supernova event that changed its destiny forever. The process begins with careful measurement. Using data from observatories on Earth and, more recently, precise measurements from the European Space Agency's Gaia spacecraft, scientists can determine Zeta Ophiuchi's proper motion, its speed and direction of travel across the sky. Combine this with its radial velocity, which is how fast it's moving toward or away from us, and astronomers can reconstruct a three-dimensional picture of its path through the Milky Way. When these calculations are projected backward in time, they reveal where Zeta Ophiuchi must have been millions of years ago, before it became the solitary runaway we see today. What emerges from this kind of analysis is compelling. Zeta Ophiuchi appears to have been born in a dense stellar nursery, likely part of a massive cluster of stars. These clusters are the cosmic cradles where giant stars like Zeta Ophiuchi form, surrounded by siblings of similar size and age. By rewinding its motion, scientists can place it back into such an environment, suggesting it once lived in a binary partnership within a bustling community of young, massive stars. Then, something catastrophic happened. The prevailing theory is that its companion exploded as a supernova, imparting a gravitational kick that flung Zeta Ophiuchi free from its birthplace. By tracing its path, astronomers can even attempt to identify the remains of that supernova, though after millions of years, the debris may have spread too thin to leave obvious signs. Galactic archaeology doesn't just satisfy curiosity about Zeta Ophiuchi's past, it also provides valuable insights into stellar populations and the dynamics of the Milky Way itself. For instance, by retracing Zeta Ophiuchi's journey, scientists can study the types of environments that produce runaway stars, estimate how often massive binaries end in such violent separations, and refine our understanding of how stars are distributed across the galaxy. Each runaway star's trajectory is like a breadcrumb trail, pointing back to the stellar nurseries where it all began. In Zeta Ophiuchi's case, this backward tracing has reinforced the idea that many runaways are ejected not just by supernovae but also through dynamical interactions within dense star clusters. When massive stars orbit each other in tight, chaotic systems, gravitational slingshots can send one or more stars flying out at high speeds. For Zeta Ophiuchi, though, the evidence points more strongly to the supernova scenario, because of its solitary nature and the velocity it attained. Its path tells a story of companionship, catastrophe, and exile, a star ripped from its home and set adrift, carrying the signature of its past like a scar. There is also a poetic aspect to this form of cosmic archaeology. On Earth, archaeologists dig through layers of soil to uncover the lives of long-dead civilizations. In the galaxy, astronomers dig through layers of space and time, reconstructing orbits and motions to uncover events that took place millions of years ago. Zeta Ophiuchi, with its runaway speed and clear trajectory, is a perfect candidate for this kind of work. Its path across the galaxy is not random, it is the imprint of history, the aftershock of a cosmic explosion that set it loose. By studying it, we glimpse not only its origin but also the violence that shaped it, a reminder that even the most beautiful stars often have turbulent pasts. And the story doesn't end with its origin. Tracing Zeta Ophiuchi's path forward into the future also has value. Just as we can calculate where it came from, we can also predict where it is going, how it will continue to carve through the interstellar medium, and where its eventual supernova will leave its mark. In this way, galactic archaeology is not just about uncovering the past, it is about placing stars into the broader timeline of the Milky Way, connecting their histories, presents, and futures into one grand narrative. For Zeta Ophiuchi, That narrative is especially compelling. It began life in a crowded stellar nursery, shared its youth with a massive companion, was torn free by a violent explosion, and now races across the galaxy, both shock blazing, toward a future supernova of its own. Without the ability to trace its path backward, we might never have pieced together this story. But thanks to the careful detective work of astronomers, we can see it not as an isolated oddity but as a traveler with a history, a star whose exile has left tracks across the Milky Way that we are only just beginning to read. As Zeta Ophiuchi barrels through the galaxy at breakneck speed, it does more than merely leave a bow-shaped glow in its wake. It fundamentally stirs the interstellar medium, creating turbulence that ripples across light years. The star's motion, combined with its ferocious stellar winds and intense radiation, sets interstellar gas into chaotic motion, compressing some regions while rarefying others. These turbulent interactions are not just visually striking, they actively shape the environment of the galaxy, influencing the birth and death of countless other stars. The bow shock that Zeta Ophiuchi produces is the most visible sign of this turbulence, a glowing arc of gas and dust pushed into high-energy motion by the star's relentless passage. Imagine a boat speeding across a lake. The water in front of it is displaced and churned, forming waves and ripples that propagate outward. On a cosmic scale, Zeta Ophiuchi does the same, but with gas clouds and cosmic dust instead of water. The star's velocity, about 24 kilometers per second, ensures that these disturbances are far from gentle. Gas clouds are compressed, creating shock fronts that heat the surrounding medium, while the density variations induced by these shocks can serve as seeds for future gravitational collapse. This is where the story becomes particularly exciting for astronomers. In regions where the interstellar medium is already dense, the extra pressure from Zeta Ophiuchi's shockwaves can tip the balance, causing pockets of gas to collapse and form new stars. In effect, this runaway star is acting as a cosmic catalyst. Its passage through space may inadvertently trigger the next generation of stellar birth, even as it hurtles toward its own inevitable death. The energy it imparts into the medium helps drive turbulence, a key ingredient in star formation, while also carving channels and cavities that reorganize the local galactic structure. Observations using infrared and radio telescopes reveal the complexity of these interactions. Dust heated by the shockwave glows in infrared, highlighting regions where gas is compressed and where turbulence is most intense. At the same time, radio observations detect variations in molecular gas density, showing areas that have been stirred or evacuated by the star's passage. Zeta Ophiuchi is, in a sense, sculpting the galaxy around it. Its winds, radiation, and motion combine to produce a dynamic environment where matter is redistributed, potentially influencing star formation thousands of light-years away from its path. Turbulence in space is not merely a local phenomenon either. Stars like Zeta Ophiuchi inject enormous amounts of energy into the galactic ecosystem. This energy contributes to the larger-scale dynamics of the Milky Way, influencing how gas clouds evolve, how spiral arms are shaped, and how the interplay of gravity and pressure governs the formation of clusters. A single massive runaway star may seem small compared to the galaxy as a whole, but its influence is multiplied by its energy output, high velocity, and extended travel through different regions of the interstellar medium. There is also an element of unpredictability. The precise effects of Zeta Ophiuchi's shockwaves depend on the density, composition, and magnetic fields of the gas it encounters. Some regions may be stirred violently, dispersing material and preventing star formation, while others may be compressed just enough to spark the collapse of gas clouds into new stars. In this way, Zeta Ophiuchi embodies both chaos and creation, a single star with the power to disrupt and the potential to give birth simultaneously. Moreover, the turbulence it produces helps scientists probe the physics of shockwaves and stellar winds under extreme conditions. By studying how gas responds to Zeta Ophiuchi's motion, researchers can test models of interstellar hydrodynamics, energy transfer, and magnetic field interactions. Every ripple, cavity, and compressed cloud serves as a laboratory, offering clues about the behavior of matter under the influence of massive stellar forces. This turbulent influence also underscores the contrast between Zeta Ophiuchi and our Sun. While the Sun's solar wind gently flows into space, shaping the heliosphere and affecting planetary environments on a much smaller scale, Zeta Ophiuchi's winds and motion create turbulence on scales that span tens of light-years. Its life is violent, its passage disruptive, and yet that very disruption may be essential to the ongoing cycle of stellar birth and galactic evolution. In short, Zeta Ophiuchi is both destroyer and creator, a wandering force that stirs the galaxy with every kilometer it travels. Through its turbulent interactions with the interstellar medium, Zeta Ophiuchi reminds us of the interconnectedness of cosmic phenomena. Stars are not isolated entities, they are engines of change. Even as Zeta Ophiuchi moves inexorably toward its own demise, it continues to shape the future of countless other stars yet to be born. Its journey is a living testament to the power of motion, radiation, and stellar winds to drive the cycles of creation and destruction that define our galaxy. Zeta Ophiuchi and the Sun are both stars, of course, but beyond that, they could hardly be more different. While our Sun seems calm, dependable, and eternal from the perspective of human lifespans, Zeta Ophiuchi is a cosmic powerhouse, burning fast and living dangerously. Comparing the two offers a dramatic illustration of the diversity of stellar lives and the wide range of fates that await stars in our galaxy. The most obvious difference is mass. Zeta Ophiuchi is roughly 20 times more massive than the Sun, a factor that determines nearly every other aspect of its existence. The more massive a star, the faster it consumes its nuclear fuel. The Sun, by contrast, has a moderate mass, which allows it to burn steadily for about 10 billion years. Zeta Ophiuchi, despite having far more fuel, will exhaust it in only a few million years. In human terms, the Sun is a lifelong steady presence, while Zeta Ophiuchi is a brilliant firecracker, blazing intensely but destined to expire quickly. That difference in mass also translates into temperature and brightness. Zeta Ophiuchi is an O-type star, with surface temperatures exceeding 30,000 Kelvin, nearly 6 times hotter than the Sun's relatively tepid 5,800 Kelvin. Its ultraviolet radiation is immense, shaping and ionizing the interstellar medium around it, while the Sun's radiation is gentle in comparison, sustaining life on Earth without fundamentally reshaping the solar system. Zeta Ophiuchi is a star that imposes itself on its environment, carving bubbles, generating both shocks, and stirring turbulence, whereas the Sun coexists in a more balanced, stable fashion with its surroundings. Their lifespans offer another point of contrast. The Sun has existed for about 4.6 billion years and will continue in its main sequence for another 5 billion. Zeta Ophiuchi, on the other hand, is probably only a few million years old, a mere infant by cosmic standards, and will meet its explosive end within a similarly brief time frame. The Sun's long, predictable life allows planetary systems to form and evolve over billions of years, providing a stable environment for life to develop. Zeta Ophiuchi's short, violent life is incompatible with long-term stability. Any planetary system it might host would be subjected to intense radiation, extreme stellar winds, and the star's eventual supernova. In other words, while the Sun is a gentle guardian, Zeta Ophiuchi is a cosmic tempest. Even their behavior in motion is telling. The Sun follows a relatively sedate orbit around the center of the Milky Way, moving in harmony with its stellar neighbors. Zeta Ophiuchi, by contrast, is a runaway, a fugitive racing through space at around 24 kilometers per second, having been ejected from its original home by the supernova of its companion. This motion alone sets it apart, creating a dynamic interplay with the interstellar medium that has no parallel in the Sun's neighborhood. Its bow shock, the turbulence it generates, and the energetic wake it leaves behind are all consequences of this high-speed flight, a stark contrast to the Sun's placid, predictable orbit. Finally, their ends are as different as their beginnings. The Sun will eventually swell into a red giant, shedding its outer layers gently and leaving behind a white dwarf, a quiet, stable remnant. Zeta Ophiuchi, however, will end in a cataclysmic supernova, potentially leaving behind a neutron star or black hole. The Sun's death will be a gentle fading, observable over millennia but unlikely to drastically reshape the surrounding region of the galaxy. Zeta Ophiuchi's death will be violent, energetic, and transformative, redistributing heavy elements, triggering shocks, and leaving its mark on the galactic environment for tens of thousands of years. The comparison highlights the incredible diversity among stars. While we often think of the Sun as representative, in reality it is a moderate, stable, long-lived star, a stellar middle class. Zeta Ophiuchi occupies the opposite extreme, massive, short-lived, tempestuous, and dramatically influential in its surroundings. One illustrates the benefits of stability, longevity, and balance. The other illustrates the raw power, the rapid evolution, and the profound environmental impact that massive stars can exert. Together, they provide a spectrum of stellar behavior, reminding us that the life of a star can be quiet and enduring or violent and fleeting, depending largely on mass, environment, and history. This contrast also underscores the uniqueness of Zeta Ophiuchi as an object of study. While the Sun teaches us about the stability necessary for life-bearing planets, Zeta Ophiuchi teaches us about the extremes of stellar evolution, the forces, energies, and interactions that shape galaxies, trigger star formation, and drive the cycle of cosmic creation and destruction. In the quiet glow of our Sun, we find familiarity and stability. In the blazing, runaway energy of Zeta Ophiuchi, we witness the universe in motion, dynamic and sometimes dangerous, revealing processes that are central to the cosmos itself. Even though Zeta Ophiuchi's bow shock is one of the most striking and well-studied features in the galaxy, it also represents a puzzle that astronomers are still trying to fully solve. A bow shock occurs when a star moves through the interstellar medium faster than the local sound speed, causing gas and dust to pile up and form a curved shock front, much like the waves a boat produces as it speeds through water. In principle, the phenomenon seems straightforward. A high-speed star plows through gas, compresses it, and heats it, producing a glowing arc visible in infrared or other wavelengths. But the reality is far more complex, and Zeta Ophiuchi's bow shock highlights just how many variables astronomers must consider. For one thing, the bow shock is not uniform. Observations show intricate filaments, knots, and variations in brightness across the glowing arc. These structures suggest that the interstellar medium itself is far from homogeneous. Gas clouds vary in density, composition, and temperature, and magnetic fields thread through them in complex ways. When Zeta Ophiuchi's wind collides with this chaotic medium, the result is not a smooth, simple shock, but a dynamic, turbulent interface that is extremely difficult to model accurately. Each observation reveals new irregularities that challenge our assumptions about how energy is transferred, how gas compresses, and how shock fronts propagate. Another complicating factor is the interplay between the star's wind, its motion, and the surrounding medium. Zeta Ophiuchi emits a powerful, continuous flow of charged particles, its stellar wind, that interacts with the interstellar gas in ways that can amplify or dampen turbulence. The angle at which the wind meets incoming material, the rotation of the star, and even variations in the wind's intensity over time all contribute to the shock structure. Computational models can approximate these interactions, but the level of detail required to fully reproduce what telescopes see is immense, and small changes in initial conditions can produce drastically different shock patterns. Temperature and ionization also introduce uncertainties. The ultraviolet radiation from Zeta Ophiuchi ionizes the surrounding hydrogen and other elements, altering how the gas responds to compression. In some regions, ionized gas can radiate energy efficiently, cooling and forming dense filaments. In others, heating dominates, inflating hot bubbles of low-density material. Observations in infrared, optical, and X-ray wavelengths each reveal different layers of this complex system, but integrating all of these into a cohesive model remains a challenge. No single observation tells the full story. Magnetic fields, invisible to the naked eye, but crucial in shaping the dynamics of the interstellar medium, add yet another layer of mystery. The interstellar magnetic field can guide and constrain the motion of charged particles, influence the shape of shock fronts, and even stabilize or destabilize filaments within the bow shock. Measuring these fields directly is extremely difficult, so much of what astronomers understand comes from indirect inference. As a result, even the best models of Zeta Ophiuchi's bow shock rely on educated assumptions, leaving room for uncertainty and ongoing investigation. Interestingly, bow shocks like Zeta Ophiuchi's also appear to be sites of particle acceleration. Some theories suggest that charged particles trapped in the shock can be accelerated to near-light speeds, producing high-energy cosmic rays. The precise mechanisms for this acceleration, and the contribution of individual bow shocks to the galaxy's cosmic ray population, are still active areas of research. Every new observation can tweak our understanding, suggesting that even a single star moving through space can influence phenomena on scales far larger than itself. In short, while the concept of a bow shock is simple, a star plowing through gas, the detailed physics is extraordinarily complex. Zeta Ophiuchi provides a natural laboratory, revealing layers of turbulent, magnetized, ionized, and heated gas interacting in ways that remain only partially understood. Each observation pushes astronomers to refine models, to account for turbulence, radiation, magnetic fields, and particle acceleration all at once. The mystery is not that both shocks exist, but that their structures and behaviors defy complete prediction, reflecting the intricate, interconnected forces that govern the galaxy. In a way, the Bow shock is a metaphor for Zeta Ophiuchi itself. On the surface, it seems like a simple runaway star creating a visible arc, but look closer, and it reveals a complexity, chaos, and power that challenges understanding. Even with decades of observation, astronomers are still learning, discovering new behaviors, and refining their theories. The Bow shock is both a signature of Zeta Ophiuchi's motion and a window into the deep, ongoing processes of stellar physics, turbulence, and cosmic energy transfer. It is a reminder that the universe rarely gives simple answers, and that even phenomena that seem understood at first glance can hold profound mysteries. Zeta Ophiuchi is already extraordinary in so many ways: its runaway speed, its massive size, its Bow shock, but the story becomes even more striking when we consider that it emits X-rays. Unlike visible light or infrared radiation, X-rays are a form of high-energy electromagnetic radiation, requiring extremely hot, energetic processes to produce them. The presence of X-ray emissions adds yet another layer to Zeta Ophiuchi's extreme and puzzling nature, signaling the intense physical conditions surrounding this runaway star and revealing processes that are still not fully understood. In massive stars like Zeta Ophiuchi, X-rays are generally associated with highly energetic phenomena in the star's outer layers and stellar winds. The intense radiation and rapid rotation of an O-type star drive supersonic winds that collide with themselves and with interstellar material, producing shocks that can heat gas to millions of degrees. These shocks, in turn, emit X-rays, acting as a natural high-energy beacon that allows astronomers to probe the most extreme conditions around the star. In Zeta Ophiuchi's case, the X-ray luminosity is significant enough to be detected from Earth, despite being hundreds of light-years away, providing a unique window into the high-energy environment of a massive runaway star. The source of these X-rays is not entirely straightforward. Some of the emission comes from shocks within the stellar wind itself, where faster-moving wind streams collide with slower ones, compressing and heating gas to extreme temperatures. Other contributions may come from the Bow shock created as Zeta Ophiuchi races through the interstellar medium, where its high-speed motion generates additional turbulence and heating. This combination of wind shocks and interstellar collisions produces a complex X-ray spectrum that astronomers can analyze to learn about wind speeds, density variations, and even the chemical composition of the material surrounding the star. X-ray observations also highlight the violent and unstable nature of Zeta Ophiuchi's atmosphere. O-type stars like it are not quiet spheres. They are dynamic, with turbulent surfaces, magnetic fields, and variable wind flows. The detection of X-rays confirms that energy is being dissipated in unexpected ways, possibly through localized magnetic reconnect ion events or small-scale shocks that produce bursts of high-energy radiation. Each X-ray photon we detect is a clue, a signal that something extraordinary is happening in a region of space that cannot be probed by visible light alone. The X-ray emissions are not just scientifically intriguing, they are a reminder of how fundamentally different massive stars are from stars like the Sun. While our Sun emits X-rays, they are relatively modest, generated by its hot corona and magnetic activity. Zeta Ophiuchi, by contrast, produces X-rays as a natural consequence of its enormous mass, extreme winds, and high-velocity motion. The star is a powerhouse, operating in energy regimes that are literally orders of magnitude more intense than those found in more moderate stars. This extreme output is part of what allows it to carve Bow shocks, stir the interstellar medium, and potentially trigger the formation of new stars. Yet it also makes the star a puzzle, as the interplay of forces producing these X-rays is complex and difficult to model completely. X-ray astronomy, then, provides a vital tool for understanding Zeta Ophiuchi. By studying its high-energy emissions, astronomers can infer wind velocities, density fluctuations, shock strengths, and even the structure of the star's magnetic field. These insights are essential for building accurate models of massive star evolution, particularly for runaway stars, whose interactions with the galaxy are more dynamic than stars that remain in their birth clusters. X-rays also give clues about the star's future, signaling how it is losing mass, how its winds interact with its surroundings, and what conditions might precede its inevitable supernova. The fact that Zeta Ophiuchi emits X-rays reinforces the sense that it is not an ordinary star, It is extreme in every measurable way. Its brightness, temperature, speed, and winds are already remarkable, but the addition of high-energy X-rays confirms that this star is a laboratory for the physics of extreme stellar environments. Each observation adds to a picture of a star that is dynamic, violent, and capable of influencing the galaxy on scales far larger than its own size. Ultimately, Zeta Ophiuchi's X-ray emissions remind us that the universe operates on scales and energies far beyond human experience. Where the naked eye sees a single, faint point of light, high-energy instruments reveal a star racked by shocks, turbulence, and radiation powerful enough to illuminate the surrounding interstellar medium in X-rays. It is a star that defies easy categorization, a runaway fugitive whose extreme nature challenges our understanding and beckons astronomers to keep studying its high-energy secrets. Despite decades of observation and study, Zeta Ophiuchi continues to guard many of its secrets, leaving astronomers with a series of unsolved questions that fuel ongoing research. Its extreme properties, runaway status, and violent past all hint at a complex history, yet the details of its formation and the exact impact of the supernova that ejected it remain shrouded in mystery. Each observation provides clues, but a full understanding of this enigmatic star is still just out of reach. One of the most fundamental questions is deceptively simple. Where exactly did Zeta Ophiuchi form? Galactic archaeology allows astronomers to trace its path backward, and evidence suggests it was born in a dense stellar nursery, likely associated with a massive cluster of young stars. However, pinpointing the precise cluster or region is complicated by the dynamics of the galaxy. Over millions of years, stars drift, clusters disperse, and interstellar gas moves in complex patterns. Even with precise measurements of its speed and trajectory, the uncertainties inherent in modeling these movements across vast distances make it difficult to definitively identify its birthplace. The trail it leaves is like footprints in sand washed by cosmic tides. Clear patterns exist, but exact locations remain elusive. Adding to the mystery is the supernova that presumably ejected Zeta Ophiuchi from its binary system. This event must have been extraordinarily powerful, imparting enough momentum to fling the star through space at its current velocity of roughly 24 kilometers per second. Yet the precise dynamics of that explosion, the mass of the companion star, the orientation of the binary system, the exact energy released, are not directly observable. Astronomers rely on models to reconstruct the scenario, but even small variations in the assumptions about the supernova can drastically change the calculated trajectory and velocity of Zeta Ophiuchi. In other words, while we can infer that a supernova occurred, the full story of how it transformed Zeta Ophiuchi's life is still speculative. Even the star's internal structure may bear scars from the supernova event. Being in a binary system that underwent such a violent disruption could have altered its rotation, magnetic fields, or surface composition. Some models suggest that massive stars ejected from binaries might experience differential rotation or other instabilities that could affect their evolution, stellar wind behavior, or eventual supernova explosion. Observations of Zeta Ophiuchi's spectrum provide hints, such as unusual abundances of certain elements or evidence of strong surface mixing, but interpreting these signs in terms of the supernova's influence is a challenge. Each data point raises as many questions as it answers. Another layer of uncertainty involves the missing companion. Astronomers know that Zeta Ophiuchi must have had a partner to explain its runaway status, but that companion has vanished, leaving only indirect evidence of its existence. Was it completely destroyed in the supernova, leaving a neutron star or black hole behind? Could remnants of it be detectable today, perhaps as a faint pulsar or a localized supernova remnant? Attempts to locate the remains are complicated by the passage of millions of years, the dispersion of debris, and the complex environment of interstellar gas in that region of the galaxy. The companion's absence leaves a gap in the story, a missing character whose actions forever altered Zeta Ophiuchi's path but whose details remain hidden. These unresolved questions are not mere academic curiosities, they affect how we understand the evolution of massive stars in general. If astronomers could fully reconstruct Zeta Ophiuchi's formation, binary history, and supernova encounter, it would provide a benchmark for models of stellar evolution, runaway dynamics, and supernova physics. Each unknown parameter, the initial mass of the companion, the distance of the binary system from the cluster, the orientation of the ejection, feeds into uncertainties in broader theories about how massive stars live, die, and influence their galactic environments. Even the interaction of Zeta Ophiuchi with the interstellar medium has unanswered elements. Its bow shock, turbulence, and X-ray emissions are observable, yet the detailed physical mechanisms driving these phenomena remain only partially understood. How exactly does its high-speed motion and wind combine with variations in the interstellar medium to produce the intricate structures seen in infrared and X-ray imaging? How much of the shockwave's energy contributes to star formation, and how much is dissipated harmlessly? These questions underscore the broader uncertainty surrounding even the most observable features of this runaway star. Ultimately, Zeta Ophiuchi exemplifies the balance between what we can know and what remains mysterious in astrophysics. We can measure its speed, mass, temperature, and radiation. We can study its bow shock, X-ray emissions, and trajectory. Yet, even with all this data, fundamental aspects of its history and evolution remain elusive. Where did it truly originate? How did the supernova change its spin, composition, or trajectory? What became of the companion that once shared its life? Each question is a reminder that the universe is not always fully legible, that stars can carry histories written in light and motion that we are only just learning to read. Zeta Ophiuchi, in other words, is a living enigma. Its violent life, runaway journey, and extreme physical characteristics make it one of the most intriguing stars in the galaxy. But its mysteries are what make it scientifically invaluable. Each new observation, from X-ray imaging to infrared mapping of its bow shock, adds pieces to the puzzle. But the complete picture remains tantalizingly out of reach, inspiring ongoing study and wonder. Zeta Ophiuchi is more than a runaway star with a violent past. It is also an agent of change in the galactic ecosystem, a key player in the ongoing evolution of the Milky Way. Stars like it, massive and short-lived, exert influence far beyond their immediate vicinity. Their radiation, stellar winds, and ultimate supernova explosions act as both destroyers and creators, redistributing matter, stirring turbulence, and enriching the galaxy with heavy elements that will seed future generations of stars and planets. In essence, stars like Zeta Ophiuchi are the gardeners of the Milky Way, shaping the galactic environment on timescales of millions of years. One of the most significant ways Zeta Ophiuchi contributes to galactic dynamics is through its intense stellar winds. Unlike the Sun's relatively gentle outflow, this O-type star generates supersonic streams of charged particles that push against surrounding interstellar gas. As the star barrels through space, these winds sweep up material, carving out bubbles and cavities in the interstellar medium. These structures can extend for tens of light-years, redistributing gas and dust that might otherwise remain static. By compressing gas in certain regions and evacuating it in others, Zeta Ophiuchi helps regulate where and when new stars can form, effectively acting as both a sculptor and a catalyst in the galactic ecosystem. The star's bow shock amplifies this effect. As it plows through the interstellar medium, the bow shock compresses gas, heats dust, and injects energy into the surrounding environment. These processes contribute to turbulence on a local scale, and the turbulence can propagate through nearby clouds, influencing star formation far from the star itself. In this sense, Zeta Ophiuchi is not a passive observer but an active participant in the life cycle of the galaxy, its motion and radiation shaping the conditions under which future stars, planets, and perhaps even life may arise. When Zeta Ophiuchi eventually ends its life in a supernova, its influence will expand to galactic proportions. Supernova. Explosions are among the most energetic events in the universe, dispersing heavy elements like carbon, oxygen, silicon, and iron into the interstellar medium. These elements are crucial for planet formation and for the chemistry of life itself. Zeta Ophiuchi's supernova will effectively seed its region of the Milky Way with the raw materials for future stars and planetary systems, continuing a cycle of cosmic recycling that has been ongoing since the galaxy's formation. The energy from the blast will also drive shockwaves through surrounding gas, compressing some clouds into star-forming regions while dispersing others, further influencing the spatial distribution of matter in the galaxy. In addition to shaping the chemical and physical landscape, stars like Zeta Ophiuchi affect galactic dynamics on a broader scale. The cumulative effect of massive stars, supernovae, and stellar winds drives large-scale turbulence and circulation within the Milky Way's spiral arms. This feedback process regulates star formation, prevents excessive gravitational collapse in gas clouds, and maintains the dynamic structure of the galaxy over millions of years. Zeta Ophiuchi, moving at high speed and generating intense radiation and shocks, is a microcosm of this larger process, illustrating how individual stars contribute to the overall ecology of the galaxy. Runaway stars add another layer of complexity. By leaving their birth clusters, they transport energy, momentum, and enriched material into regions of the galaxy that might otherwise remain unaffected. Zeta Ophiuchi's journey as a galactic exile spreads the influence of its birth cluster and its supernova far and wide. Its motion allows for the distribution of energy and matter across vast distances, influencing not just its local neighborhood but potentially triggering star formation or altering the dynamics of gas clouds hundreds or thousands of light-years away. This process of stellar recycling and galactic shaping highlights the interconnectedness of stars, gas, and dust. No star exists in isolation. Zeta Ophiuchi's life, from its formation to its supernova, demonstrates the feedback loops that govern the Milky Way's evolution. Its radiation sculpts gas clouds, its winds drive turbulence, and its eventual explosion seeds future generations. Each massive star contributes to a larger story, one of transformation, renewal, and the continuous flow of matter and energy through the galaxy. In studying Zeta Ophiuchi, astronomers gain insight into these processes in ways that more ordinary stars cannot provide. Its extreme mass, velocity, and winds make its impact on galactic dynamics visible and measurable. By observing the bow shock, tracing its motion, and modeling its future supernova, scientists can see firsthand how a single massive star interacts with the Milky Way on both local and global scales. In doing so, they begin to understand how the galaxy maintains its structure, regulates star formation, and perpetuates the cycle of cosmic life and death. Ultimately, Zeta Ophiuchi is not merely a runaway star, it is a dynamic agent in the galaxy, a star whose existence and actions ripple through the Milky Way. Its journey, its violent energy, and its eventual demise all contribute to the ongoing processes that govern stellar birth, evolution, and death. In this way, it serves as a vivid reminder that the cosmos is not static but alive with forces and interactions that shape everything from the smallest dust grains to the spiral arms of the galaxy itself. When we step back and consider Zeta Ophiuchi in the grand tapestry of the cosmos, it is impossible not to feel a profound sense of perspective. Here we are on Earth, a tiny blue dot orbiting an average star, while Zeta Ophiuchi, a single star, blazes through the Milky Way with a mass 20 times that of the Sun, speeds exceeding 50,000 miles per hour, and energy capable of shaping entire regions of interstellar space. It illuminates a scale of cosmic forces that dwarfs our everyday experience, reminding us just how small and fragile our world truly is in comparison to the vast machinery of the universe. Even the distances involved are staggering. At approximately 366 light-years away, Zeta Ophiuchi is far beyond the reach of human travel, yet its winds, radiation, and eventual supernova will ripple across tens of light-years of interstellar medium, affecting matter thousands of times larger than the volume of our solar system. To imagine the bow shock alone, the glowing arc tens of light-years across, is to recognize that the scale of phenomena in space is almost incomprehensible. A single star, moving through space, can influence clouds of gas, trigger the birth of new stars, and inject energy into regions of the galaxy far larger than anything on Earth. Our planet, and even our entire solar system, are infinitesimal specks compared to the forces at work here. The energy output of Zeta Ophiuchi amplifies this perspective. Every second, the star emits immense amounts of radiation, including intense ultraviolet light and high-energy X-rays, while its stellar winds propel charged particles into space at millions of kilometers per hour. Over the course of a human lifetime, the cumulative energy radiated by Zeta Ophiuchi would dwarf all human energy consumption, not just on Earth but across the entire planet, many times over. It is humbling to realize that the star's natural processes produce energies that we can barely comprehend, yet they are routine for a star of this mass and type. Moreover, its future supernova places Earth and humanity into a cosmic frame of scale and risk. While 366 light-years is safely distant, the eventual explosion will release energy equivalent to billions of times the Sun's annual output, briefly outshining entire regions of the galaxy. The shockwaves, heavy elements, and high-energy radiation will disperse across vast distances, reshaping interstellar space. From our vantage point, we might see it as a spectacular celestial event, but on a galactic scale, it is merely one of countless stars undergoing birth, life, and death in a cycle that has persisted for billions of years. Zeta Ophiuchi's drama reminds us that the forces shaping galaxies operate on scales far beyond the human experience of time and space. The star also underscores the dynamic nature of the galaxy itself. While our Earth seems anchored and motionless in our everyday perception, the Milky Way is a seething, ever-changing environment. Stars orbit the galactic center, clouds of gas swirl and collapse, and massive stars like Zeta Ophiuchi plow through their surroundings, triggering turbulence and recycling matter. In this context, the solar system is like a tiny boat on a vast, stormy ocean. Zeta Ophiuchi is one of the massive waves crossing that ocean, illustrating the scale and power of the galactic forces at play. Contemplating this scale can be both humbling and inspiring. It reminds us that while human concerns dominate our perception of reality, they are infinitesimal compared to the forces shaping galaxies. A star like Zeta Ophiuchi lives and dies in ways that profoundly impact its surroundings, while Earth continues its quiet orbit in relative safety, yet entirely insignificant in the cosmic scheme. Understanding this perspective fosters a sense of awe, as we recognize that the universe operates on scales of energy, distance, and time that are almost impossible to intuitively grasp. Finally, considering Earth's smallness relative to stars like Zeta Ophiuchi invites reflection on our place in the universe. We are observers, capable of measuring, modeling, and comprehending the physics of massive stars and turbulent galactic environments. Yet our home planet is minuscule, vulnerable, and fleeting in comparison. The runaway star's motion, energy, and eventual death provide a vivid reminder that the universe is alive with forces that dwarf us in every conceivable way. It is both a humbling and exhilarating realization. Earth is tiny, human lifespans are brief, and yet we have the tools and curiosity to witness and understand the magnificent, violent, and beautiful processes unfolding in the cosmos. Zeta Ophiuchi, in all its glory, violence, and mystery, acts as a mirror to our smallness. The bow shocks, the turbulence, the X-rays, the runaway velocity, all these phenomena illustrate a scale so immense that they make our world seem almost inconsequential, yet they also highlight the power of observation, imagination, and scientific inquiry. Through our telescopes, simulations, and studies, we bridge the gap between human scale and cosmic scale, finding understanding and wonder in a universe where stars like Zeta Ophiuchi remind us of how vast and dynamic the galaxy truly is. Zeta Ophiuchi's story reaches its most dramatic form when we consider its entire journey. A star forged in a crowded stellar nursery, bound once to a massive companion, violently cast into exile by a supernova, and now racing across the Milky Way with a bow shock blazing like a cosmic emblem of its past. It is, in every sense, a wanderer, a star unmoored from its birthplace, carrying the scars and imprints of a violent history, yet still full of energy, mystery, and potential for further transformation. Unlike stars that live quietly in their clusters, Zeta Ophiuchi's life is a narrative of movement, impact, and extreme physics, a story written across tens of light-years of interstellar medium and millions of years of cosmic time. Its journey is as visually spectacular as it is scientifically rich. The glowing bow shock, captured in infrared by the Spitzer space telescope, paints an image of a star literally plowing through gas and dust at immense speed, creating a cosmic shield that stretches across light-years. Its X-ray emissions, turbulent winds, and ultraviolet radiation reveal the forces at play in ways that our imaginations can scarcely grasp. This star is not static. It shapes and reshapes its environment with every kilometer it travels, injecting energy, stirring turbulence, and redistributing matter that will one day contribute to the formation of new stars. Zeta Ophiuchi's passage through the galaxy is a living demonstration of how single massive stars can exert influence far beyond their own mass and size. Yet behind this brilliance and violence lies a story shrouded in uncertainty. The supernova that ejected it remains an unseen specter, the missing companion a ghostly absence whose identity and fate are still mysteries. Astronomers can trace its path backward, reconstruct its trajectory, and model the forces at work, but the full details of its origin and the exact consequences of its cataclysmic separation remain elusive. Zeta Ophiuchi, in many ways, guards its past like a starry sphinx, revealing hints while withholding complete understanding. Every new observation adds a piece to the puzzle, yet every discovery also raises further questions, maintaining the aura of enigma that surrounds it. Its future is equally compelling and dramatic. The star's enormous mass and short lifespan mean that it will not endure for long by cosmic standards. In a few million years, It will exhaust its nuclear fuel and explode in a supernova, an event so energetic it will briefly rival the luminosity of entire star clusters. That explosion will release shockwaves, stir interstellar gas, and enrich its surroundings with heavy elements, the building blocks of planets and life, continuing the cycle of creation and destruction that defines the galaxy. There is even the remote possibility of a gamma-ray burst, a narrow beam of extreme radiation that, if aligned with Earth, could have profound consequences. Though improbable on a human timescale, the potential underscores the immense power locked within this runaway star. What makes Zeta Ophiuchi truly extraordinary is the combination of its past, present, and future. It is a star shaped by catastrophe, defined by motion, and destined for an explosive finale. Its bow shock traces the path of its journey, its turbulent winds reshape its environment, and its eventual supernova will leave an indelible mark on the Milky Way. Yet despite all that we know, the star remains a source of mystery. The exact circumstances of its ejection, the fate of its companion, the full complexity of its bow shock, and the subtleties of its high-energy emissions all remain open questions. It is a reminder that even in a universe increasingly understood through observation and theory, some cosmic actors retain a sense of secrecy, complexity, and awe. Zeta Ophiuchi is more than a point of light in the night sky. It is a narrative of stellar evolution made manifest, a living laboratory for the physics of massive stars, a sculptor of interstellar gas, and a herald of cosmic power. It reminds us of the vast scales of distance, energy, and time that govern the galaxy, dwarfing human concerns yet offering glimpses into processes that ultimately shape the universe itself. From its violent past to its energetic present and its cataclysmic future, Zeta Ophiuchi embodies the raw, dynamic, and often unpredictable nature of the cosmos. In the end, this runaway star is a wanderer in both space and story. It challenges our understanding, captivates our imagination, and exemplifies the extremes to which the universe can operate. It moves through the Milky Way like a cosmic traveler with a tale of violence, survival, and inevitable transformation. A star whose life is both a spectacle and a mystery. As we observe it, model it, and trace its path across the galaxy, we are reminded of our smallness, our curiosity, and the endless wonders that lie beyond our world. Zeta Ophiuchi keeps many of its secrets hidden, but in doing so, it continues to inspire wonder, fuel scientific discovery, and illuminate the intricate dance of stars, gas, and gravity that defines our galaxy. In this way, Zeta Ophiuchi is not just a star, it is a storyteller, a force of nature, and a living testament to the majesty and mystery of the universe. Its journey from violent beginnings to an explosive destiny encapsulates the drama of the cosmos, a reminder that even a single star can shape galaxies, sculpt interstellar matter, and leave a legacy that resonates across light years and eons. In the grand theater of the Milky Way, Zeta Ophiuchi is a star that refuses to be ordinary, a cosmic wanderer, a powerful sculptor of space, and a reminder that the universe is always far more vast, violent, and wondrous than it seems from the tiny vantage point of Earth. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.